There's a galaxy so large it makes the Milky Way feel like a single pixel, IC1101, a colossus that seems to swallow everything we call home. It's not just bigger, it's a different kind of object stitched together by dark matter, ancient mergers, and violence on unimaginable scales. So what does largest galaxy even mean? And if IC1101 can grow this vast, what else is the universe quietly building beyond our intuition? Out there, the universe plays a cruel trick on the human mind. Distance becomes a substance, and scale becomes a verdict. When we chase a record, we risk finding something stranger than a winner, a new way to measure reality itself. Tonight, we leave the comfort of familiar maps and enter a realm where edges are negotiated, not drawn. A galaxy can look complete in one image, then unravel into a ghostly outskirts when the exposure deepens. In the case of IC1101, the headline is only the doorway. The real story is the argument hiding inside the word largest, because galaxies are not solid objects with walls. They're gradients of starlight, swarms of dark matter, and histories written in orbits, each one offering a different answer. So we will ask a sharper question. What exactly counts as a galaxy's size when the universe refuses to provide a clean boundary? Is it the bright body you can trace with confidence, the faint halo that barely rises above the sky, or the invisible mass that holds everything together? To follow that question, we have to become careful observers, not just awed ones. We have to understand how astronomers draw isophotes through near darkness, how scattered light can imitate structure, and how a single choice in data reduction can move an edge by hundreds of thousands of light years. But this is not merely a tale of measurement, it is a tale of environment. IC1101 does not live alone. It sits in a crowded metropolis of galaxies, immersed in a thin furnace of X-ray, hot gas, surrounded by a gravitational landscape dominated by dark matter. In a place like this, growth is not a simple act of accumulation. It is a slow negotiation between time, motion, and the relentless bookkeeping of gravity. And then, just as starlight seems to define the limits, another kind of structure intrudes, one that cares nothing for the distribution of stars. From the vicinity of a supermassive black hole, jets can lance outward and inflate lobes across intergalactic space, sketching a galaxy's reach in radio light where optical images show almost nothing. Across this journey, we will watch largest fracture into competing rulers, luminous extent, gravitational domain, and cosmic influence, each grounded in different physics, each with its own uncertainties. The deeper we look, the more the universe forces a choice. Do we want a single champion, or do we want the truth behind the scoreboard? Because IC1101 is not only a giant, it is a test of our language, our instruments, and our intuition. An object that asks whether the boundary between a galaxy and a cluster is a line, or a fade into the dark. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We will begin by unmaking our sense of scale, then step into the cluster that builds giants, and finally confront the many definitions of an edge. Along the way, we'll meet the forces that assemble stellar empires, and the engines that can project a galaxy's power far beyond its light. Start with a familiar map of size, because comfort is part of the trap. Earth is a sphere of rock and water, and its whole history fits inside one thin atmosphere. From orbit, the air is a pale rind, fragile, luminous, and easy to forget. The continents look permanent, but the planet's surface is a moving skin of plates. Even the oceans, which feel endless from shore, are a shallow film on a cooling world. The moon is close enough to feel like a neighbour, yet far enough to make distance real. Its cratered face holds the scars of impacts that Earth's weather erased. In the black between them, you can imagine the 3-day journey of Apollo, an era when distance became a number, not a myth. The moon's pull also writes itself into our seas, a quiet reminder that gravity reaches across emptiness. The solar system widens fast, past the orbits we memorized, into a dark where sunlight weakens. Past Mars, the light thins, and the warmth becomes a memory carried by instruments. Jupiter's realm is a stormy giant, and beyond it the outer planets circle slowly in long cold years. At the edge the heliosphere fades, an invisible bubble where the solar wind yields to interstellar space. Even here, scale still feels like travel, like time, like a route you could trace. Then the frame jumps outward until the sun becomes a point and the planets become bookkeeping. Distances stop behaving like roads and start behaving like physics. Light years replace kilometers, and the mind resists the swap. The nearest stars appear as a sparse fog, and the Milky Way begins to take shape as a disk. The bright band we see from Earth becomes a flattened city of stars, threaded with dark lanes of dust. We call it a galaxy, and imagine a border, as if starlight draws a clean edge. But the Milky Way is not a coin with a rim. It is a rotating system with spiral arms, a central bar, and a halo of older stars. The Milky Way is about 100,000 light-years across in its bright disk, and that number already strains intuition. It holds hundreds of billions of stars, and it still feels like a home. Now make the Milky Way an inset. Keep it visible, but stop letting it dominate the picture. Place it beside a galaxy so large that the comparison feels like a mistake. This is IC 1101, a name that sounds like a catalogue entry because it is one. It was recorded in surveys that turned the sky into a ledger, where wonders arrive as coordinates. It sits far away in the constellation Serpens, anchored in the dense heart of a galaxy cluster. It is often described as the largest galaxy ever found, and that phrase is both useful and dangerous. IC 1101 is not a single simple object with one agreed boundary. It is a layered structure, built by gravity over billions of years, and its outer parts fade into the cluster itself. In deep images, the core looks like an enormous elliptical glow, smooth and almost featureless. Then, as the exposure deepens, faint light keeps appearing, like mist revealing a coastline that never quite ends. Still, the headline numbers are hard to ignore. Estimates put it near 100 trillion stars, roughly 100 times the Milky Way's stellar count. That estimate depends on how bright the galaxy is, how far away it truly sits, and what kinds of stars dominate its light. Its visible stellar body can extend to about 550,000 light-years across, depending on how deep you measure. Beyond that, a diffuse halo of stars and intra-cluster light may reach toward 4 million light-years. At that scale, language starts to overreach. You may hear the claim that IC 1101 would swallow our entire universe, because the mind wants a single shocking comparison. The science says something more precise, and more unsettling in its own way. Its extended halo could engulf the local group, the small association that includes the Milky Way, Andromeda, and dozens of dwarfs. The local group is not the entire universe, and correcting that matters, because this film is about definitions. The poetic claim hooks us, but the accurate claim reveals the real mystery. The mystery is not only that IC 1101 is huge, the mystery is that nature permits such huge structures to assemble at all, without tearing themselves apart. It forces a question that sounds simple until you try to answer it. What does it mean to call something the largest galaxy, when galaxies do not end at a wall? What do we measure when the outer light is faint, the boundaries are statistical, and the mass is mostly invisible? From the start, we need 3 different meanings of size because each one tells a different story. First is the luminous extent, the region where starlight is bright enough to map confidently. This is the size most people picture, and it is the easiest to photograph. It depends on exposure depth, background subtraction, and how you define a surface brightness limit. In practice, astronomers trace isophotes, contours of equal brightness, until the signal dissolves into noise. 2 astronomers can use the same telescope and report different diameters, because the edge is a choice. Second is the stellar halo and the intracluster light, the diffuse population of stars that drifts beyond the main body. These stars can be stripped from smaller galaxies during close passes, or scattered by mergers, or liberated by tidal forces in the cluster core. Many of them no longer orbit a single galaxy in a neat way. They roam the cluster's central potential, like embers carried by a shared wind. The halo is real, but it is faint, and it blends into the glow of the surrounding cluster. Measuring it means fighting noise, modelling the sky, and deciding what belongs to the galaxy versus the cluster. Flat field errors, scattered light, and foreground stars can masquerade as a phantom halo. Observers subtract the background with extreme care, because the signal is often a tiny fraction above the sky. In the biggest systems, that distinction becomes less like a line and more like a debate. Third is the dark matter halo, often summarized by a virial radius, a scale tied to gravity rather than light. This is the invisible architecture that holds the system together and guides its growth. The virial radius is not a physical shell you could hit. It is a statistical boundary where the system is roughly gravitationally relaxed. Plainly, where the galaxy's gravity has had time to organize matter. We infer it through galaxy motions, gravitational lensing, hot gas temperatures, and simulations that connect mass to structure. Each method carries its own assumptions. Galaxy velocities can be biased by orbits that are not fully settled. Lensing measures mass directly, but it depends on geometry and the alignment of background galaxies. Yet, it may be the most meaningful size because it tells us how far the galaxy's gravity dominates. These three sizes will recur throughout the film because they explain why the word largest is slippery. A galaxy can be enormous in starlight, but modest in dark matter, or vice versa. A galaxy can have a bright core and a vast faint envelope that changes with every new observation. A galaxy can also be the central condensation of a much larger cluster-scale halo, making the galaxy and its environment inseparable. IC 1101 sits exactly at that boundary where categories begin to fail. The stakes are not just semantic. If the largest galaxies live at the centers of clusters, then their size is a record of the universe's long-term behavior. Gravity has a long memory, and it keeps receipts. It remembers every merger, every disrupted satellite, every stream of stars pulled into a new orbit. It remembers the slow assembly of what we can call cosmic cities, where thousands of galaxies share one deep gravitational well. IC 1101 is a central dominant galaxy, the kind that grows by being in the right place for a very long time. In a cluster core, smaller galaxies orbit through dense space, lose energy, and spiral inward. That loss is not magic. It comes from dynamical friction, where a moving galaxy drags a wake through dark matter and stars, and the wake tugs back. Some galaxies are torn apart before they reach the center, donating stars to the intracluster light. Some merge directly, adding mass to the central galaxy and puffing up its outer regions. Over billions of years, the center becomes a graveyard of past galaxies, and the boundary between one galaxy and many becomes blurred. The core can remain smooth because violent events happened long ago, and because random motions erase sharp features. Yet in the faint outskirts, you might still find shells, streams, and subtle asymmetries, fossils of encounters that have not fully mixed away. In a sense, the outer light is a time machine, but it speaks in whispers. This is why the phrase cannibal galaxy appears in the literature, even if it sounds dramatic. The growth is not fast, and it is not violent in the human sense. It is slow, statistical, and relentless, driven by dynamical friction and tidal stripping. The result can be a galaxy with a normal-looking core and an outer envelope so extended that it challenges our measurement tools. IC 1101 is a candidate for the extreme end of that process, and it forces us to ask whether we are seeing one galaxy or the central light of a whole cluster. The numbers are impressive, but they are also a warning about uncertainty. 100 trillion stars is an estimate, not a census, derived from brightness, distance, and models of stellar populations. Those models depend on the initial mass function, how many small stars exist compared with large ones, because small stars add mass without adding much light. 550,000 light-years for the visible body depends on where you draw the isophote and which data set you trust. 4 million light-years for the diffuse halo depends on separating a faint signal from a complicated background. In the largest systems, the error bars are not an afterthought, because the edge is the question. So when we say IC 1101 could engulf the local group, we are not claiming a literal swallowing in the way a planet swallows a moon. We are comparing extents, and extents depend on definitions. The local group spans a few million light-years, and its galaxies are separated by large empty volumes. A diffuse halo of stars and intracluster light can overlap that scale, even if the density is extremely low. In such a halo, the night sky would not blaze with stars. It would look almost empty, yet gravity would still be keeping count. That tension between poetic scale and scientific precision is the engine of this documentary. We need the poetry because it breaks complacency, and we need the precision because it reveals the mechanism. The mechanism is not only stars, it is dark matter shaping where stars can gather, and hot gas tracing the depth of the gravitational well. In clusters, that gas can reach tens of millions of degrees, glowing in X-rays like a weather map of gravity. It is also feedback from supermassive black holes whose jets can heat gas and regulate star formation, changing how a galaxy grows. Size is not one number because growth is not one process. Some growth is hierarchical, small systems merging into larger ones over cosmic time. Some growth is environmental, clusters providing a steady supply of satellites to strip and absorb. Some growth is suppressed, heated gas refusing to cool into new stars, leaving a galaxy to expand mostly by rearranging existing ones. When we look at IC1101, we are seeing the outcome of all these channels layered together. In the coming chapters, we will keep returning to a simple, uncomfortable idea. The Milky Way is not a standard unit, and our sense of normal is parochial. Our galaxy is a mid-sized spiral in a modest group, not the template for what galaxies can become. At the centers of rich clusters, the rules of accumulation change because the supply of material is larger and the timescales are longer. IC1101 is a clue to that regime, and it may not be unique. We also have to confront what we mean by galaxy itself. Is a galaxy defined by where most of its stars are, or by where its gravity binds matter? Is it defined by a visible boundary, or by a statistical overdensity in a sea of cluster light? When a central galaxy's halo blends into intracluster light, are we seeing an object or an environment? These are not philosophical distractions because they change how we count mass and how we test cosmological models. There is history behind this discomfort. Early catalogues treated nebulae as smudges, and only later did we learn they were island universes, galaxies beyond our own. Now, with deep surveys and sensitive detectors, the problem has inverted. We can see so far into the faint outskirts that the old clean categories start to dissolve again. Each improvement in imaging pushes the boundary outward, and each push forces a new definition. IC1101 sits in a cluster called Able 2029, and that context is not optional. The cluster is filled with hot gas that shines in X-rays, and it contains hundreds to thousands of galaxies. The cluster's dark matter halo is vastly more massive than any single galaxy, and it sets the stage for extreme growth. The central galaxy is where orbits decay, where mergers accumulate, and where the brightest light collects. If we want to understand the largest galaxies, we have to understand the largest gravitational wells that host them. So Chapter 1 ends with a reframe scale and an open problem. IC1101 is enormous by any everyday standard, but its exact size depends on what you measure. Luminous body, diffuse halo, dark matter halo, each one tells a different truth. The claim that it could swallow the local group is a useful shock, but it is not the whole story. The real story is how a universe governed by gravity builds structures that make our definitions wobble. To understand IC1101, we must first understand the environment that builds it. That means galaxy clusters, intracluster light, and the deep wells of dark matter that shape everything inside them. We move next from one extreme galaxy to the cosmic city that raised it. Chapter 1 left us with a problem that sounds simple until you try to measure it carefully. IC1101 looks like a single galaxy, yet its edge behaves like a choice. The boundary is not a sharp shoreline, and it is not a clean mathematical curve either. It is a fading of light into darker light, and then into the sky itself. A camera does not record galaxy, and not galaxy, as separate categories. It records photons, and at the outskirts there are very few of them. Out there, every count matters, because the signal is comparable to the noise from sky glow and instrument scatter. The faintest halo lives in a regime where subtraction and calibration become part of the story. So the question is not only what IC1101 is, but where it stops being itself. That uncertainty is not a mistake. It is the signature of its environment. To understand IC1101, we move outward before we move inward. The largest galaxies almost never grow alone, because the universe rarely feeds them in isolation. We begin with the setting that makes giants possible, and we treat it like a landscape. The landscape is a galaxy cluster, and it is the largest gravitationally bound city the universe builds. A cluster is not just a crowd of galaxies in the same frame. It is a single structure, bound together by gravity, that can persist for billions of years. In wide-field images, clusters look like constellations that have fallen inward. Bright ellipticals sit like lanterns, while spirals drift in the outskirts like suburbs. If the camera lingers, you can almost feel the depth. points of light arranged not on a flat page, but in a three-dimensional swarm. The center looks crowded, yet the emptiness between galaxies is still immense. The scale is difficult to hold in the mind because the distances between galaxies are immense. Even in a dense core, galaxies are separated by tens of thousands of light years. That separation is why direct collisions between stars are vanishingly rare, even when galaxies overlap in images. What interacts is gravity, whole stellar systems tugging on other stellar systems across intergalactic space. Yet the cluster is still a city, because the same gravity governs every orbit within it. Each galaxy is a resident, moving in a shared gravitational address. A typical rich cluster contains hundreds to thousands of galaxies, but that census is only the visible population. The dominant mass is not in stars, and it is not even in gas. The dominant mass is dark matter, and it outweighs everything we can see by a wide margin. In many clusters, dark matter accounts for most of the total mass budget. Dark matter is not a fog of ordinary particles, and it does not shine in any wavelength we can capture. We infer it through its gravity, because gravity leaves tracks even when light does not. Those tracks show up in the motions of galaxies, which move too fast to be held by visible matter alone. They also show up in gravitational lensing, where mass bends background light into arcs and subtle distortions. In a sense, lensing lets us see the cluster's mass without seeing the mass itself. The sky behind the cluster becomes a screen, and the cluster becomes a warped lens. In deep images, the most dramatic lenses look like bright crescents and mirrored smears around the core. In more common cases, the effect is quieter, tiny shears that only statistics can reveal. That statistical lensing is painstaking work because it depends on measuring the shapes of thousands of background galaxies. The reward is a mass map that does not care whether the matter is luminous. In a cluster, dark matter shapes the overall potential like invisible terrain. Galaxies move through that terrain as if on rails, guided by a map we cannot photograph. The map is not smooth like a bowl made of glass. It is clumpy and layered, built from smaller halos that merged over cosmic time. That history matters, because clusters are not born fully formed. They assemble gradually as filaments of the cosmic web funnel matter into knots. If you could watch the universe from far above, you would see streams of galaxies flowing along those filaments. The cluster would look like a junction where many roads meet. Those roads are not metaphorical, because simulations show matter flowing along preferred directions, set by the early universe's density fluctuations. The cluster's present-day shape still remembers those ancient imbalances. The cluster is also filled with a second, often overlooked component. Between the galaxies sits the intracluster medium, a vast reservoir of thin plasma. This gas is not like the air in a room, and it is not like the gas in a spiral galaxy's disk. It is so tenuous that a cubic centimeter can contain far fewer particles than the best laboratory vacuum. Even so, the volume is enormous, and the total mass of this plasma can rival the mass locked in stars. The cluster is, in part, a giant atmosphere held down by gravity. This gas is heated to tens of millions of degrees by the cluster's gravity. As it falls inward, gravitational potential energy turns into thermal energy, and the plasma becomes a high-temperature sea. At those temperatures, it glows in X-rays, turning the cluster into an object of high-energy light. In visible images, the space between galaxies looks empty, but in X-rays it is luminous. An X-ray telescope does not see stars as points of light in the same way optical cameras do. It sees a diffuse glow whose brightness depends on density, because denser plasma emits far more strongly. X-ray images do not just show gas. They trace pressure and temperature, which trace the depth and shape of the gravitational well that confines the plasma. The logic is simple in plain terms. Hotter gas needs a deeper gravitational well to keep it from escaping. When we measure the gas temperature and distribution, we infer the mass required to hold it. This method leans on a physical assumption called hydrostatic equilibrium, where gas pressure balances gravity on average. It is not perfect, but in relaxed clusters it becomes a powerful way to weigh the invisible. In relaxed clusters, the hot gas can settle into a smooth distribution around the center. The X-ray glow becomes rounder, and the brightest region often marks the deepest part of the potential. In disturbed clusters, it shows ripples, shocks, and asymmetries that record recent collisions. Those features are not artistic textures. They are physical scars from mergers between clusters or subclusters. Some ripples are sound waves travelling through the plasma driven by activity in the core. Some shocks are like cosmic weather fronts, where gas is compressed and heated by supersonic motion. If the visuals were translated into sound, those ripples would be low, slow notes, stretched over hundreds of thousands of light years. The cluster is not silent. It is simply operating on scales our senses were not built for. Clusters are not quiet collections of galaxies. They are long-lived engines where orbits, gas and gravity interact over billions of years. The timescales are slow, but the energies are extreme. A cluster merger can release more energy than any supernova, simply because the masses involved are so vast. At the center of the richest clusters, the biggest galaxies are usually central dominant galaxies. They sit where the potential is deepest, where infalling matter is hardest to escape. Astronomers call them brightest cluster galaxies, or BCGs. Many are also CD galaxies, ellipticals with enormous diffuse envelopes that extend far beyond the bright core. The term CD has a history, and it reflects how unusual these systems looked when they were first categorized. Early observers saw a normal elliptical, and then a faint extended extra component that seemed to belong to something larger. That classification grew out of mid-20th century photographic surveys, when astronomers began to notice that some cluster centers were not just brighter. They were structurally different, with halos that refused to end where ordinary ellipticals ended. That extra component is the envelope, and it is the source of much of our confusion. It can extend hundreds of thousands of light years, with light so faint it competes with the sky background. Those envelopes matter because they blur the boundary between a galaxy and its environment. In a cluster core, the outer light can be more like shared weather than private property. When you look at a CD envelope in deep imaging, it can resemble mist around a mountain. The core is the peak, but the haze spreads across the valley, touching other peaks. And in the deepest exposures, the mist is not perfectly smooth, because it carries subtle seams, shells, plumes, and gradients that hint at past arrivals. The city keeps its receipts, but it writes them in faint starlight. The cluster encourages runaway growth through a slow but persistent mechanism. It is called dynamical friction, and it turns orbital motion into heat in the background medium. The phrase sounds technical, but the idea is intuitive if you picture a boat moving through water. The boat makes a wake, and the wake pulls back, draining energy. A massive galaxy moving through dark matter and stars creates a gravitational wake. That wake pulls backward, stealing momentum and orbital energy from the moving galaxy. The wake is not made of gas waves alone. It is an overdensity of matter, dark matter and stars, that is gravitationally focused behind the moving galaxy. In more formal terms, the moving mass perturbs the background distribution function, and the resulting asymmetry exerts a net drag. The galaxy slows, its orbit shrinks, and the cluster's center becomes an attractor. The effect is weak on any single pass, but it accumulates over cosmic time. Massive satellites spiral inward, like a slow snowfall of galaxies into the deepest valley. The inward spiral is not a straight fall, and it is not a dramatic plunge. It is a gradual tightening of the orbit, measured in billions of years, as energy leaks away. Dynamical friction is most effective for the most massive satellites, which is why the center preferentially collects big pieces. Smaller galaxies can orbit for a long time, like pedestrians circling the city rather than moving to the courthouse. As satellites sink, some merge with the central galaxy. Others are shredded by tides, donating their stars to a diffuse population that no longer belongs to one orbiting system. Tidal forces are strongest where the gravitational field changes rapidly with distance, which is exactly what happens near the cluster core. A satellite can be stretched and pulled apart, and its stars can be scattered into long streams. Those streams can persist for a while, like pale ribbons in the dark. Over time, repeated encounters and the cluster's overall potential mix them into a smoother glow. That mixing is a kind of dynamical weathering, where coherent structures are erased by many small perturbations. The cluster does not need one catastrophic event. It can dissolve identity through repetition. That diffuse population is intracluster light. It is made of stars stripped during encounters, scattered during mergers, and liberated by the cluster's tidal field. Intracluster light is not a decorative detail. It is a record of violence spread thin, and it is a clue that the cluster itself is building a central glow. In deep exposures, intracluster light can look like a faint aurora around the core. It is not centered on any one galaxy perfectly, and that is part of the point. Some of those stars may have been born in small galaxies long ago, then removed before their original homes were fully destroyed. Others may have been tossed outward during mergers, like sparks thrown from a grinding wheel. There is a quiet implication here that is easy to miss. Clusters do not only rearrange galaxies, they also redistribute stars into a population with no galaxy at all. The city creates its own streetlights. This is why the word largest becomes slippery in cluster centers. The central galaxy grows by mergers, but it also grows by reclassifying stripped stars as part of its halo. The physics that builds a BCG also hides its true outline. The outer envelope is extremely faint, and it competes with the brightness of the sky and the complexity of the background. Even a perfect telescope must contend with Earth's atmosphere, scattered light in optics and subtle gradients in the detector. The outer halo lives where those imperfections begin to matter. A single bright star outside the frame can scatter light into broad wings, and those wings can masquerade as a galaxy's envelope. Even the telescope's point spread function becomes a character in the plot. To measure a giant halo, astronomers set a surface brightness limit. They trace isophotes until the signal fades into noise, then decide where the galaxy effectively ends. An isophote is simply a contour of equal brightness, like a topographic line on a map. In the bright core, those contours are easy to draw, but in the outskirts they become uncertain and fragile. At large radius, the isophotes can twist or flatten, and that geometry can hint at accretion history. A smooth ellipse suggests long mixing, while subtle distortions can betray recent additions. That decision is not arbitrary, but it is not unique either. Different instruments, reduction methods, and sky models can shift the boundary by hundreds of thousands of light years. One sky subtraction can remove too much and erase real halo light. Another can leave too much and accidentally assign background glow to the galaxy. This is why observers spend so much effort modeling the sky, masking contaminating sources, and checking for systematic gradients. The measurement is not only about photons, it's about controlling every way photons can be miscounted. A galaxy can appear to grow when the data get deeper. The stars were always there, but the measurement finally reaches them and the reported diameter expands. This is not a loophole in science. It is a reminder that faint structure is real structure, and that our definitions depend on what we can reliably detect. In the early days of extragalactic astronomy, galaxies were often described by what could be seen on photographic plates. As detectors improved, the universe did not change, but the catalogued sizes and halos did. That history is part of why famous largest claims can shift from decade to decade. The competition is not only between galaxies, it is between observing techniques and the limits they can push. Clusters intensify this problem because the background is not empty. The cluster core contains overlapping halos, scattered light, and intra-cluster stars that form a shared luminous fog. This fog is not uniform and it is not static. It can be lopsided from recent accretion, or threaded with barely visible streams from disrupted galaxies. So we have to ask a question that will follow us through the film. Is the biggest galaxy a single object, or is it partly the cluster's central light wearing a galaxy's name? Now we place IC1101 into its address. It sits at the centre of Abell 2029, one of the most massive and well-studied clusters in the nearby universe. The name Abell carries its own history tied to the era when astronomers began to map clusters systematically. Rich clusters were catalogued as signposts of large-scale structure, and Abell 2029 became one of the standout entries. George Abell built his catalogue from photographic survey plates, counting galaxies and estimating richness by eye and by careful criteria. It was an early step toward treating clusters as a population with statistics, not just curiosities. Abell 2029 lies roughly 1 billion light-years away, on the order of a few hundred megaparsecs. That distance is not just space, because light travel time turns it into time. When we observe Abell 2029, we observe it as it was about 1 billion years ago. The photons arriving now left before many events on Earth's surface had even begun. The night sky, then, is not a window onto the present. It is a layered archive, where distance becomes a kind of timestamp, and that timestamp is not perfectly crisp, because distance itself must be inferred through redshift and cosmological models. Even the act of placing the cluster on a timeline depends on how we measure the expansion of the universe. Look-back time does not mean the cluster is frozen. It means we see a past state, and we must reconstruct the present by combining physics with many snapshots across distance. We compare clusters at different distances to infer an evolutionary sequence, but we must do it carefully. A far cluster is not literally the ancestor of a near cluster, yet the physics links them. At that scale, even the word nearby is relative. 1 billion light-years is close enough for detailed study, yet far enough that small errors in distance affect every derived size. If the distance estimate shifts, the inferred diameter shifts with it. Even the brightness profile can be reinterpreted, because physical scale depends on the conversion from angle to length. Able 2029 is also a clean laboratory for cluster physics. It has a strong X-ray signal, indicating a deep potential and a large reservoir of hot intracluster gas. In X-ray views, the cluster can appear as a glowing, centrally concentrated cloud. The brightest region often coincides with the BCG, like a beacon marking the bottom of the gravitational well. The glow is not merely pretty, because its shape encodes the cluster's dynamical state. A smooth, symmetric core suggests long settling, while offsets and edges can indicate recent disturbance. In such clusters, the gas wants to cool in the dense center. Cooling would let it condense, form stars, and feed the central black hole. But the story rarely stays that simple. Cooling is not a metaphor here, but a measurable loss of thermal energy through radiation. The plasma emits X-rays, and that emission carries energy away, which should lower the temperature over time. If cooling proceeded unchecked, the central gas would become denser, and the cooling would accelerate. The core could develop a classic cooling flow, delivering material toward the center. Yet many clusters do not show the expected levels of star formation that such flows would produce. Something is interrupting the cycle, and the interruption is one of the most important clues in cluster astrophysics. Feedback interrupts the cooling cycle. Jets and outflows from the central supermassive black hole can reheat the gas, inflate cavities, and keep star formation suppressed. In X-ray images, those cavities can look like dark bubbles carved into the glow. They are not empty, but filled with relativistic particles and magnetic fields, pushed outward by the black hole's activity. Around the bubbles, bright rims can appear where gas is compressed, and weak shocks can propagate outward as the cavities expand. The cluster core becomes a thermostat. Cooling tries to turn down the heat, and the black hole turns it back up. The jets do not need to be constant to matter. Episodic outbursts can deliver enough energy to offset cooling, maintaining a delicate balance over long time scales. This matters for growth, because it changes what kind of growth is possible. If gas cannot cool efficiently, the central galaxy gains mass mainly by mergers, not by new star formation. That distinction shapes the galaxy's appearance. A galaxy built by new star formation would show bright young populations, but BCGs are dominated by older, redder stars. Their spectra and colours point to stellar populations formed early, when the universe was more gas-rich. Later, the cluster environment favours assembly over birth, adding stars that already exist rather than making many new ones. Dry mergers build size faster than they build brightness. They add stars to the outskirts, puff up the envelope, and increase the radius without creating many young blue stars. The word dry means gas poor, and it is a key qualifier. Without much cold gas, the merger is more like a gravitational rearrangement than a star-forming fireworks display. In simulations, repeated dry mergers can dramatically expand a galaxy's effective radius. The central density changes modestly, while the outer halo becomes more extended and more diffuse. That is one reason BCGs look smooth and old. Their stars formed early, then the galaxy expanded later by rearranging and accreting already formed stellar systems. The cluster's dark matter halo sets the stage for all of this. It defines the velocities of galaxies, the temperature of the gas, and the rate at which orbits decay. High velocities in clusters can make mergers less common for typical galaxies, because fast encounters do not easily bind. The center is different, because dynamical friction slows the most massive satellites and increases the chance of capture. The cluster core is where the potential is steepest. It is where dynamical friction is most effective, and where tidal forces are strong enough to peel galaxies apart. Over time, the central galaxy becomes a collector of remnants. Its outer halo becomes a mixing zone where streams dissolve into a diffuse glow that is hard to assign. In that mixing zone, you can ask a deceptively simple question. Which stars are truly bound to IC 1101, and which are merely passing through the center on cluster orbits? The answer depends on orbital energy and on the shape of the potential, but it also depends on what we can measure. At 1 billion light-years, individual stellar motions are beyond reach, so we rely on light profiles and statistical traces. Sometimes those traces are globular clusters or planetary nebulae, used as test particles in the halo. They are faint, but they can extend far and they can hint at where the galaxy's influence thins into the clusters. This is the environment that can produce an extreme object like IC1101. It is not just a big galaxy, but the central condensation of a much larger gravitational system. Even the label CD hints at the ambiguity. The extended envelope can be so large that it resembles a cluster component, yet it is still brightest at the center. That brightness peak is important because it anchors the identity of the galaxy. The core is unmistakably a galaxy, dense with stars and likely hosting an enormous black hole. But the outskirts are where the story becomes mysterious. The light keeps going, and the contours keep expanding until they begin to overlap with the cluster's own glow. So what do we mean when we say IC1101 is the largest galaxy ever found? Do we mean the brightest central core, the widest measurable halo, or the full region influenced by its gravity? Chapter 1 introduced 3 sizes that refuse to agree. Here, the cluster explains why those sizes diverge most strongly in the bigger systems. The luminous size depends on surface brightness limits and data depth. The halo size depends on how we separate galaxy light from intracluster light in a crowded core. The dark matter size depends on a different boundary entirely. It is tied to a virial radius and to the cluster scale halo, not to the starlight we can trace. The virial idea is a way of defining where a system is gravitationally settled. It draws a boundary based on average density and dynamical equilibrium, which is useful for halos but not directly visible. In practice, that boundary is often defined by an overdensity threshold relative to the critical density of the universe. It is a convenient line for theory and simulations, even though nature provides only a gradual transition. In Abell 2029, the cluster halo is the dominant structure. IC1101 sits inside it, and its stars occupy the deepest region of a much larger dark matter landscape. This is why central galaxies are special. They do not just orbit inside the city, they sit at City Hall, where every road eventually leads. The metaphor holds because the center is where matter accumulates. Orbits decay inward, gas pressure peaks, and feedback cycles are most intense. It is also why the biggest galaxies are almost always BCGs. The cluster provides a steady supply of satellites, and gravity provides a long timescale to process them. The supply is not uniform and it is not random. Galaxies arrive along preferred directions, guided by filaments, and the central region records that history in its structure. Sometimes the record is visible as a slight elongation of the envelope, aligned with the cluster's large-scale shape. Sometimes it is hidden in the kinematics we can only infer, where different components may rotate or drift differently. The result can look like runaway growth, but it is really cumulative advantage. The center starts massive, then becomes more massive because mass makes sinking easier for others. This is one of the quiet rules of hierarchical structure formation. Bigger objects have deeper wells, and deeper wells are better at collecting even more material. If we could watch Abell 2029 over billions of years, we would see a slow inward drift. We would see mergers that add bulk, and stripping that adds haze, and both would inflate the envelope. We would notice that some encounters are clean mergers, while others are grazing passages that peel off stars. The central light would grow not only by addition, but by redistribution. We would also see that the boundary between IC1101 and Abell 2029 is not a wall. It is a gradient in density and in orbital allegiance fading from galaxy to cluster. That gradient is visible in the way the light profile changes slope at large radius. It is also visible in the way the cluster's X-ray glow remains extended far beyond the galaxy's brightest regions. The gradient is the source of the documentary's tension. The headline wants one monster galaxy, but the physics keeps hinting at a hybrid object. So we hold 2 ideas at once. IC1101 is a galaxy with a central core and a long history of mergers. IC1101 is also a name we give to the brightest part of a cluster's shared stellar fog. The 2 statements are not contradictions, but they force us to be precise. Precision is difficult because the universe does not label its components for us. We impose categories, galaxy, halo, intracluster light, because categories help us reason. Yet in the densest environments, nature does not respect our boundaries. The cluster core is a place where matter is continuously exchanged, and identity becomes a gradient. There is an almost philosophical question hiding inside the data reduction. When does ownership begin, and when does it dissolve into commons? The answer is partly physics and partly the conventions we agree to use. The central question returns with sharper edges. How can structures grow so large without breaking? And what does largest mean when the environment is part of the object? When we say breaking, we mean dynamical stability and coherence over time. A giant galaxy must remain gravitationally bound, even as it is repeatedly disturbed by mergers and tidal encounters. The fact that it does remain bound tells us something about the depth of its potential and the role of dark matter. It also tells us that growth can be gentle in its own way, even when it's violent locally. The cluster-scale engine is now in view. We have the city, the invisible mass that shapes it, the hot gas that reveals it, and the slow friction that feeds its center. Now that the cluster-scale engine is in view, we step into IC 1101 itself. We examine its structure, its light profile, and the evidence behind the numbers that made it famous. As we move inward, keep the city in mind, because the city is always present in the background. Every faint photon at the edge of IC 1101 carries a question. Is this starlight a private possession or a shared civic glow? And as the camera tightens on the core, another question follows. If the outskirts are ambiguous, what does the center reveal about the history that built this giant? Now that the cluster-scale engine is in view, we step into IC 1101 itself. The camera does not meet a pinwheel of arms or a crisp dust lane, but a pale, continuous oval, like a lantern seen through fog. At first glance, it reads as a single, smooth ellipse, with no spiral arms to count and no obvious bar to anchor the eye. The bright center dominates the frame, and the light falls outward in a calm gradient that seems almost deliberate. Even the color feels restrained, as if the galaxy has traded drama for mass and memory. Yet that calm is not stillness, and it is not the order of a spinning disk. It is the signature of random stellar motion, not a coherent rotation pattern that would carve out arms. In giant ellipticals, stars orbit in many directions at once, and the overall shape stays smooth because the motions average out. The galaxy is supported by velocity dispersion, pressure in the dynamical sense, rather than by a single fast-turning plane. If we could speed up time, the galaxy would look like a swarm rather than a wheel. Individual stars would loop on boxy, tilted and elongated paths, constantly crossing and recrossing the center. Some orbits would be almost radial, plunging inward and then coasting back out into the halo. The system holds together because gravity sets the rules, even when the orbits do not share a single plane. This is why the image feels so different from a spiral like the Milky Way. A disk galaxy advertises its angular momentum, while an elliptical hides it inside a pressure-supported stellar soup. The difference is dynamical and historical. Ellipticals are often the end state of repeated mergers that scramble ordered rotation. In that sense, the smoothness is not a design, but an aftermath. Astronomers reconstruct this structure by measuring surface brightness as a function of radius, turning a photograph into a quantitative profile. They fit isophotes, those contour lines of equal brightness, and they track how each contour's ellipticity and orientation change with distance. They correct for the telescope's point spread function, because even perfect optics smear light outward and can fake a larger core. They also account for cosmological surface brightness dimming, because at IC 1101's distance, the universe itself makes diffuse light harder to see. The work is meticulous because the signal is not uniform across the galaxy. In the inner region, the signal is strong and the profile is stable across instruments, filters, and observing nights. In the outskirts, every assumption about background and scattered light can shift the result, sometimes by more than the faint halo itself. The outer measurements live in a regime where a tiny gradient in the sky can masquerade as a physical structure. So the reduction pipeline becomes part of the story. Astronomers mask foreground stars and background galaxies, subtract the sky, and test how sensitive the profile is to each choice. They model the sky with obsessive care, because a tiny error across a wide field becomes a false envelope. They run alternate reductions, compare independent datasets, and ask a blunt question. Does the halo survive when we change the rules? Even the telescope matters in a way viewers rarely consider. Wide-field cameras help because they measure the background far from the galaxy, while narrow fields can confuse galaxy light with sky glow. Internal reflections, detector flat field imperfections, and the wings of bright stars can all leak into the low surface brightness regime. At these levels, the galaxy competes with the instrument's own fingerprints, ghosts that must be recognized and removed. IC1101's anatomy is usually described in 3 layers, and the layered description is more than a metaphor. There is a dense core, a broad elliptical body, and an extended low-surface brightness envelope that keeps going. Each layer corresponds to a different balance of gravity, history, and measurement difficulty. Each layer also changes how we think about what the word galaxy is allowed to mean. The core is where the galaxy's stellar density peaks, and where the gravitational potential is steepest. It is also where we expect the strongest imprint of a central black hole, because the black hole's influence is most concentrated there. In a visual sense, the core is the part that refuses to be ignored, even when the rest fades. On screen it is a bright knot, a concentrated glow that seems to hold the whole system in place. But the core is not always a simple bright cusp. In giant ellipticals, the core can show a central light deficit relative to a smooth inward extrapolation of the outer profile. That deficit is often interpreted as scouring by a binary supermassive black hole, a kind of gravitational excavation. The missing light is not an absence of matter, but a rearrangement, stars pushed outward by repeated encounters. The idea is straightforward even if the dynamics are complex. 2 black holes sync after a merger, form a bound binary, and eject stars through repeated gravitational slingshots. Each close encounter transfers orbital energy to passing stars, flinging them outward and lowering the central density. Over time, the binary hardens, the core expands, and the galaxy's center is quietly hollowed. The process leaves a measurable imprint, like a footprint pressed into the brightness profile. If IC1101 grew through many major mergers, its center should carry that history in its geometry. A large core would be a fossil of repeated black hole pairing, dynamical heating, and the slow erasure of steep cusps. The core becomes a memory, written not in words but in missing starlight. It is a reminder that even darkness can be evidence. Outside the core, the main body follows the classic behavior of an elliptical light distribution. It is often approximated with a Cercic profile, where the slope changes gradually with radius rather than breaking sharply. The Cercic index becomes a compact summary of how concentrated the galaxy is and how extended its wings are. In practice, the index is a shorthand for structure that would otherwise take paragraphs of numbers to describe. A high Cercic index implies a steep central concentration and an extended outer wing, so the galaxy fades slowly at large radii. In practice, the fit is a way to compress a complicated structure into a few parameters that can be compared across samples. It is also a reminder that the eye can be fooled. What looks uniform can hide multiple components. The fit is not the galaxy, but it is a disciplined way to interrogate the galaxy. Then the profile breaks from what ordinary ellipticals tend to show. A faint envelope appears as excess light above the inward extrapolation of the main profile, and the curve refuses to fall as fast as expected. The excess is subtle in images, but unmistakable in the mathematics. On a plot, it looks like a stubborn shoulder, refusing to drop into darkness. That excess is why IC1101 is classified as a supergiant elliptical and often as a CD galaxy. The CD label points to a central dominant galaxy with a diffuse, overgrown halo, as if the galaxy has spilled beyond its own boundaries. Historically, CD galaxies were recognized because their outer light seemed too large to be explained by a single elliptical component. The term emerged in the era when photographic plates first made these halos hard to ignore. The classification is not only about size, but about context and structure. CD envelopes are strongly associated with brightest cluster galaxies in rich, relaxed cluster cores, where the gravitational potential is deep and long-lived. In that environment, the central galaxy becomes a collector of mass, of satellites, and of stripped stars. The cluster is not merely a neighborhood, but a machine that feeds the center. In IC1101, the envelope is the part that turns a big galaxy into a measurement problem. It extends far beyond the radius where typical ellipticals become hard to trace, and it does so in the same direction the cluster itself extends. The galaxy and its environment begin to rhyme. What looks like a halo can also be the first hint of a larger shared glow. To make the scale concrete, we return to a familiar yardstick, because numbers alone can become abstract. The Milky Way's bright disk is about 100,000 light-years across, and that already feels enormous when mapped against our night sky. Its star-forming arms, gas lanes, and dust all fit inside that span. Even our galaxy's faint stellar halo, though larger, still feels like a separate component around a clearly defined disk. IC 1101's visible stellar body is often quoted up to about 550,000 light-years across. That number depends on how deep the data go, which filter is used, and which surface brightness threshold is chosen. It is not a ruler laid across space, but a contour traced through a fading glow. When the threshold changes, the contour slides outward like a tide line. The phrase visible stellar body is doing important work here. It means the region where starlight is confidently detected above background, not a physical wall in space. The galaxy does not end like a shoreline, because gravity does not draw crisp coastlines. What ends is our confidence, which is a scientific quantity as real as any measurement. Beyond that, some studies describe a halo or envelope reaching toward about 4 million light-years. That outer extent is not a single agreed diameter, because the boundary is fuzzy by nature and because the light is close to the sky level. At those radii, we are chasing photons that arrive like whispers. The difference between signal and artifact becomes a matter of method, not of desire. In the outer halo, detection becomes a contest against systematics rather than raw exposure time. Flat field errors, scattered light, and imperfect masking can mimic a false glow, and the human desire to see structure can become a bias. The faintest parts of galaxies are where instrumentation and interpretation meet. This is also where the most interesting physics can hide, because the outskirts preserve the record of assembly. So astronomers define an edge by convention, and conventions matter because they shape headlines. They pick an isophote level, a signal-to-noise requirement, and a background model that can be defended under scrutiny. The resulting diameter is a statement about data quality as much as it is about the galaxy. In the literature, the footnotes often carry as much meaning as the number. Change the threshold and the galaxy grows or shrinks on paper. The stars do not move, but the definition of measurable starlight shifts under our feet. This is where the central question returns in a practical form. What does largest mean when the object's size depends on where we stop counting photons? And what does it mean when the boundary is set by our instruments rather than by nature? The core, by contrast, is less ambiguous, and it anchors the identity of IC 1101. It is a bright, compact region that behaves like a galaxy in any reasonable definition, even if the outskirts blur into the cluster. When observers compare datasets, the core is the part that lines up first. It is the fixed point in a system that otherwise dissolves into gradients. We cannot weigh IC 1101's black hole directly with resolved stellar orbits at this distance. The sphere of influence, where the black hole dominates the stellar motions, is too small to resolve cleanly from hundreds of megaparsecs away. Instead, we use scaling relations that connect black hole mass to galaxy properties we can measure. Those relations are empirical bridges built from nearby galaxies where the dynamical evidence is clear. One relation ties black hole mass to stellar velocity dispersion, often called the M-sigma relation. Another ties it to bulge mass or luminosity, which is easier to measure but more model-dependent. Both relations were built from nearer galaxies, then extrapolated into the regime where IC 1101 lives. Extrapolation is always a wager, and the stakes rise with every order of magnitude. Brightest cluster galaxies often sit above the naive expectations of these relations, and the scatter is large. That uncertainty is part of the mystery, not a flaw to hide, because it may reflect different growth histories. If mergers build the outer envelope efficiently, the black hole may not grow in lockstep with the starlight. The center and the outskirts can keep different books. Still, the expectation is clear in direction, if not in exact number. A galaxy this massive likely hosts an extremely massive black hole, possibly in the billions of solar masses, and perhaps higher depending on the calibration. The center is not merely decorative, it is a dynamical engine. Even if we cannot see the event horizon, we can see the consequences of its gravity. That matters because the center is not only a marker of mass, it is a potential engine of feedback that can regulate gas cooling in the surrounding cluster core, shaping what the galaxy can become. In the cluster environment, the black hole is not isolated. It interacts with a reservoir of hot gas on enormous scales. The galaxy's fate is tied to the thermodynamics of the cluster's atmosphere. Feedback is how a black hole influences a galaxy far beyond its own event horizon. Jets and outflows can heat gas, inflate cavities, and prevent new stars from forming, even when the gas would otherwise cool. In X-ray images of cluster cores, these cavities appear as dark bubbles carved into the hot intracluster medium. Radio observations often trace the same regions, revealing lobes that match the voids like invisible lungs. The physics is energetic but not mystical. As matter falls toward the black hole, gravitational energy is converted into radiation and mechanical power, and some of that power couples back to the gas. The result is a thermostat, imperfect, variable, and sometimes violent, that can keep the core from condensing into a starburst. The thermostat does not have to be perfect, only persistent over cosmic time. This connects to another defining trait of giant ellipticals. They're often described as red and dead, meaning dominated by old stars with little ongoing star formation. The phrase is blunt, but it captures a measurable reality in spectra and colours. In a deep image, the galaxy's light is warm and steady, not mottled by blue clusters of newborn stars. The redness comes from stellar populations that formed early and have aged. Massive blue stars die quickly, leaving longer-lived redder stars to dominate the light, especially in the optical bands. When astronomers disperse the light into a spectrum, they see absorption features that indicate old, evolved stars. Those features also encode metallicity, the chemical enrichment that earlier generations of stars left behind. The deadness is not literal, but it is measurable in gas content and star formation rate. In cluster centers, cold gas is scarce and hard to keep, because the environment is hostile to fragile reservoirs. Even when molecular gas is detected, it is often patchy and regulated by feedback. The galaxy can still accrete material, but it rarely converts that material into a bright new generation. The cluster environment helps quench star formation through several channels, and the channels can work together. Ram pressure can strip gas from infalling galaxies, and the hot intracluster medium prevents fresh cooling by keeping gas ionized and buoyant. Tidal interactions also stir galaxies, loosening stars and gas alike. The cluster behaves like a grinder, removing the raw material for star formation and redistributing it into the intracluster medium. Even when gas reaches the center, feedback can keep it hot. The result is growth by assembly rather than by birth, dominated by dry mergers that add stars without igniting new ones. Dry mergers are quieter in color but dramatic in structure. They thicken the galaxy's outer layers, building radius with surprisingly little change in the central glow. Dry mergers add stars without adding much new light from young populations, so the galaxy grows without turning blue. They tend to puff up the outer regions, increasing radius faster than they increase central density. This is one reason the biggest galaxies can be surprisingly diffuse at large radii. The outskirts become a low-density archive, made of stars that were born elsewhere. This is a key clue to IC 1101's scale. Its enormous envelope implies a long history of accretion and rearrangement, not a long history of recent star formation. The galaxy's outskirts are a ledger of past captures, written in faint starlight. If we could tag each star by origin, the halo would look less smooth and more like a map of stolen continents. So how do astronomers get from light to a star count like 100 trillion, a number that sounds like science fiction? They start with the total luminosity, convert it to stellar mass, then divide by an average stellar mass. Each step is grounded in physics, and each step carries uncertainty. The final number is a translation, not a direct inventory. The first step requires distance and photometry. The galaxy's apparent brightness becomes an absolute luminosity only after we adopt a cosmology and a redshift-based distance, including corrections for the expansion of the universe. Even small changes in distance propagate into luminosity, because brightness falls with the square of distance. K corrections also matter, because the observed filter samples a different part of the spectrum in the galaxy's rest frame. The second step requires a mass-to-light ratio, which depends on the stellar population. Older metal-rich populations have higher mass-to-light ratios than younger, bluer ones, because they contain many low-luminosity stars and remnants. Population synthesis models translate observed colors and spectra into plausible mass-to-light values. Those models fold in stellar evolution tracks, supernova yields, and the fading of populations over billions of years. Those models are not arbitrary, but they are not uniquely determined either. They depend on how star formation proceeded, how quickly it shut down, and how metals accumulated over time. In massive ellipticals, Alpha element enhancement can signal rapid early star formation, which affects the inferred ages and masses. The chemistry becomes a clock, but it is a clock that must be interpreted. The third step requires an assumption about the initial mass function, the IMF. The IMF sets how many low-mass stars exist, and low-mass stars add mass with little light. A bottom-heavy IMF can raise the mass estimate substantially, even when the galaxy's luminosity stays the same. This is why debates about the IMF are not academic. They change the inferred weight of the universe. This is why the star count is not a census. It is a model-dependent inference that can shift by factors of several, with different population assumptions, especially in the most massive systems. When we hear a single number, we should imagine a range behind it. The uncertainty is not a weakness, but a boundary on what the data can honestly support. Dust is another uncertainty, though ellipticals are usually dust-poor compared with spirals. Even small amounts of dust can bias luminosity estimates if not accounted for, especially near the center, where dust lanes can hide in the glare. Infrared observations help, but they introduce their own calibration challenges. The irony is that the cleanest-looking galaxies can still conceal subtle obscuration. Metallicity gradients also matter, because the outer envelope can have different stellar populations than the core. If the outskirts are built from stripped satellites, their stars can be more metal-poor and slightly bluer, changing the mass-to-light ratio with radius. The galaxy becomes a composite of many smaller histories. The halo's color, if we can measure it, becomes a clue to how the envelope was assembled. A single mass-to-light ratio for the whole galaxy is a simplification. It is useful, but it hides the fact that the galaxy is a layered archive of different origins, mixed together by gravity over billions of years. The core may be enriched and dense, while the envelope may be diluted by accreted debris. In a sense, the galaxy is a museum whose exhibits have been rearranged until the labels no longer match. So the headline number of roughly 100 trillion stars is best treated as an order of magnitude estimate. It communicates scale, while the uncertainty keeps the story honest and scientific. The real lesson is not the exact count, but the fact that we can even attempt such a conversion. We're turning a smear of light into a physical population, using the rules of stellar evolution as our dictionary. The same caution applies to size, which is often presented as if it were a single property. A quoted diameter like 550,000 light-years is tied to a chosen isophote, and a deeper image can push that boundary outward. In astronomy, better data can literally make objects bigger. The galaxy does not inflate, but our ability to trace it improves. For the outer halo, the uncertainty is even more fundamental. At some point, the light is no longer clearly bound to the galaxy, and it becomes intracluster light. The transition is gradual, and it challenges the categories we use. The boundary is not an edge, but a negotiation between definitions. Intracluster light is made of stars that have been stripped from satellites or scattered during mergers. They can orbit the cluster potential rather than any single galaxy, drifting through the core like a shared stellar mist. Their distribution carries information about how violently the cluster assembled. In simulations, the intracluster component grows as the cluster matures, a diffuse witness to every close passage. In the center of a rich cluster, the CD envelope and intracluster light can overlap. The profile becomes a gradient in density and in orbital allegiance, not a clean boundary between ownership and exile. A star's path may take it through the central galaxy, while still belonging to the cluster's larger potential. The same photon can be counted as galaxy light, or as cluster light, depending on where we draw the line. This is the tension we cannot resolve with a single photograph. When we say IC 1101 has a halo out to millions of light-years, we're also asking where the cluster begins. The words galaxy and cluster become less like nouns and more like approximations. The deeper we look, the more our categories start to fray. Astronomers try to separate these components by looking for changes in the light profile slope. A transition can suggest where the galaxy-dominated component yields to a cluster-dominated one, even if the change is subtle. They also examine how the ellipticity and position angle behave, because intracluster light can align with the cluster's overall shape. A twist in the isophotes can be a quiet hint that the environment has taken over. They also use tracers like globular clusters and planetary nebulae when possible. These objects can extend far and provide kinematic hints, even when the diffuse light is too faint. Velocities can reveal whether the outskirts move like a galaxy halo or like a cluster population. Kinematics, when available, turns a brightness debate into an orbital one. But at IC 1101's distance, the data are limited and interpretations compete. Some analyses favour a very extended envelope, while others argue for more conservative boundaries that avoid contamination. The disagreement is a sign of difficulty, not a sign of carelessness. When the signal is a whisper, even honest methods can disagree about what they heard. Competing measurements do not mean the science is failing. They mean the object sits near the limits of what surface photometry can robustly define, where systematic errors rival the signal. In that regime, skepticism is part of the method. The careful scientist becomes a critic of their own pipeline, not just a user of it. This is why IC 1101 is such a powerful example for the film's central question. It forces us to admit that size is not one number, but several definitions in tension, each with its own logic. The galaxy is large in every sense, but the exact magnitude depends on what we mean by large. The uncertainty is not a footnote, it is the point. Light defines one kind of size, tied to detection thresholds and stellar distribution. Gravity defines another kind of size, tied to mass and to the surrounding dark matter landscape. A galaxy can be compact in light yet extended in mass, or extended in light yet embedded in something larger. The two definitions overlap, but they are not identical, and IC 1101 sits where the mismatch becomes visible. To connect those, we need an independent way to probe mass that does not rely on starlight. This is where gravitational lensing enters as a second line of evidence, using the universe itself as an optical experiment. Mass bends space-time, and space-time bends light. The effect is subtle in weak lensing, but it is relentless, and it accumulates across the sky. In strong lensing, mass produces obvious arcs and multiple images of background galaxies. In a Bell 2029, the more common tool is weak lensing, which is subtle and statistical rather than dramatic. The distortions are small enough that no single galaxy image convinces you, but thousands together do. The signal emerges only when patterns rise above random orientations. Weak lensing measures tiny, coherent distortions in the shapes of many background galaxies. From those distortions, astronomers reconstruct a projected mass map of the cluster, including uncertainties and smoothing scales. The method demands careful calibration because the atmosphere, optics, and detectors also distort shapes. It also requires a clean separation between background sources and cluster members, because mixing them dilutes the signal. That map includes dark matter, hot gas, and stars, all at once. It does not care what is luminous, only what bends space-time along the line of sight. In that sense, lensing is a democratic probe, everything with mass votes. It is one of the few tools that can weigh the invisible without asking it to shine. Lensing helps separate the mass of IC 1101 from the mass of Abell 2029, at least in a statistical sense. It clarifies whether the outer regions are galaxy-dominated or cluster-dominated, and it constrains how steeply the mass profile rises. Even when the light becomes ambiguous, the gravity can remain measurable. The lensing map becomes a second portrait, drawn in curvature rather than in photons. It also reminds us that the largest mass component is not the galaxy's stars. The cluster's dark matter halo is the main structure, and IC 1101 is embedded within it like a bright knot in a much larger web. The galaxy is central, but it is not alone. Its brilliance is a tracer of a deeper, darker architecture. So IC 1101's outer envelope is not only a personal halo, it is also a record of the cluster's central history, written in stars that may no longer belong to anyone in particular. The envelope becomes a boundary object, part galaxy, part cluster. The farther out we go, the more the story shifts from identity to relationship. This is what seedy halos imply about formation. They suggest repeated accretion of satellites, tidal stripping in the core, and long-term mixing in a deep potential well. Over time, the central galaxy grows not just by merging, but by harvesting what the cluster's tides loosen. The cluster supplies the raw material, and the center becomes the repository. The envelope is a kind of archaeological layer. Each disrupted galaxy contributes stars, and the combined light becomes smooth only after time erases the sharp edges. Phase mixing and violent relaxation blur streams into a diffuse glow, turning past collisions into present serenity. The smooth halo is not a lack of events, but the result of many events blended together. In that sense, smoothness is not simplicity. Smoothness can mean the violence happened long ago, and the system has had time to relax, settling into an equilibrium that hides its origin. The galaxy's calm face can be the mask of ancient turbulence. If we could peel back the smoothing, we would see a history of impacts. Yet even in relaxed systems, the outskirts can preserve faint shells and streams. Those features are hard to see at 1 billion light-years, but they are expected in the physics and seen in nearer ellipticals. The question becomes not whether they exist, but whether our instruments can reveal them here. And if we cannot see them, we must still account for what their absence might mean. So the guided tour becomes a guided argument, and each region supports a different part of the case. The core tells us the galaxy is real and dense, and the centre likely hosts an extreme black hole. The main body tells us the system is an elliptical built from old stars with little cold gas. The light is steady, the colours are mature, and the dynamics are scrambled. The envelope tells us the galaxy is also a collector, inflated by dry mergers and stripping. It tells us that growth can be additive and diffuse, building size without rebuilding youth. The halo tells us something more unsettling, because the farther out we look, the less IC 1101 resembles an object with an edge. The galaxy becomes less like a thing and more like a transition. Instead, it begins to resemble a gradient, a slow fade from galaxy to cluster. At some radius, the question stops being about measurement technique and becomes about ontology. Are we tracing a galaxy's outskirts, or the cluster's shared stellar sea? When the light is that faint, the boundary becomes a philosophical choice backed by statistics. The answer can be both, depending on which definition of belonging we use. Bound orbits, surface brightness thresholds, and catalogue conventions do not always agree, and each definition carries a different intuition. A star can be near the galaxy and still be dynamically claimed by the cluster. In a deep potential well, proximity is not the same as ownership. This is why the phrase "largest galaxy ever found" is both useful and dangerous. It is useful because it forces attention, and dangerous because it implies a clean boundary that nature may not provide. IC 1101 is large enough to expose the seams in our language. It makes us confront how much of astronomy is definition and how much is discovery. If we define size by bright starlight, IC 1101 is enormous but still finite in a practical sense. If we define size by faint halo light, it can expand toward cluster scales, and the number becomes sensitive to our choices. If we define size by dark matter, we confront the fact that the dominant halo is the clusters. Each definition is defensible, and each tells a slightly different story. Then the galaxy's identity becomes inseparable from its environment, and that is the deeper mystery. The central giant is not merely sitting in the cluster, it is entangled with it, exchanging matter and sharing a gravitational stage. In that entanglement, the concept of an edge becomes less like a fact and more like a decision. The galaxy is not just in a place, it is made by that place. So the tour ends where the mystery deepens. The more carefully we look, the more IC 1101 becomes a transition zone between galaxy and cluster, a luminous threshold rather than a closed object. The image fades outward, and the definition fades with it. We are left with a boundary that behaves like twilight, not like a wall. To understand how such a transition zone forms, we rewind time and follow the growth of giant galaxies through cosmic history. To understand how such a transition zone forms, we rewind time and follow the growth of giant galaxies through cosmic history. In the beginning, the universe is almost smooth, yet it is never perfectly uniform. Tiny imbalances in density, seeded in the earliest moments, become the blueprint for everything that follows, and their imprint is preserved like a fossil in later structure. Gravity amplifies those differences, because slightly denser regions pull in slightly more matter, and the advantage compounds as expansion stretches everything else apart. In plain terms, the universe starts with faint wrinkles, and those wrinkles deepen into structure. On screen, the first visual is subtle, a near black field with a soft, mottled texture. Then the contrast increases, as if an invisible hand is turning up the gain, and the mottling begins to look less like noise and more like terrain. What looked like static becomes geography, and the geography becomes a map of future galaxies, traced in gradients too small to notice at first glance. This is the era when dark matter matters most, because it collapses first and sets the scaffolding, while ordinary gas is still pressured by heat and radiation. The early density field is not random in the everyday sense, even though it is statistically described. It carries a characteristic pattern of fluctuations that cosmologists measure in the cosmic microwave background, a relic glow released when the universe became transparent. Those fluctuations are tiny, parts in 100,000, yet they are enough, because gravity needs only a slight head start to produce enormous contrasts later. Over billions of years, they collapse, connect, and stretch into the cosmic web, guided by the way matter flows down gradients in the gravitational potential. If we pause on that idea, the web is not drawn by hand, and it is not a decorative overlay. It is the natural outcome of an expanding universe where gravity competes with cosmic stretching, and where dark matter provides most of the mass. The first halos form where peaks in the density field exceed a threshold, and then they grow by accreting surrounding material. In simulations, this looks like a slow, relentless gathering, as if the universe is learning where to put its weight. The web has three dominant features that repeat across scales, from tens to hundreds of millions of light years. Filaments are elongated highways of matter and galaxies, where gravity channels flows along preferred directions, and where gas can be shock-heated as it streams inward. Nodes are intersections where filaments meet, and where mass piles up into the deepest wells, eventually forming groups and clusters. Voids are the expanding low-density regions between them, where growth is slow and the universe looks almost empty, even though dark matter still threads through. Visually, filaments appear as faint luminous threads in a vast darkness, with galaxies like dew on a spiderweb. Nodes glow brighter, not because they shine more per star, but because they hold more stars, more gas, and more gravitational binding energy. Voids feel like silence, a cosmic negative space that makes the dense region seem even denser, and the emptiness becomes part of the composition. The pattern is not decorative. It is the consequence of gravity acting on an expanding universe, with initial conditions set long before any star existed. Clusters form at nodes because gravity pulls along the filaments toward the deepest wells. Gas, dark matter, and galaxies stream inward, not as a sudden flood, but as persistent flow, and the directions of arrival preserve the geometry of the web. The inflow is anisotropic, meaning it prefers certain directions, because the filaments guide it like channels in a watershed. The result is a long-term convergence that keeps feeding the same centers, and those centers become the natural homes of the biggest galaxies. A cluster is not a snapshot of crowding. It is a junction that has been collecting for most of cosmic time. Even when a cluster looks relaxed, it is still accreting at its outskirts, still digesting smaller groups that arrive as coherent packets. The core is the oldest part, and it remembers the longest history of infell, because the earliest arrivals had the most time to sink inward. In that core, the conditions are extreme enough to change how galaxies live and to blur the line between a galaxy and its environment. This is the first rule behind IC 1101's scale. The biggest galaxies are usually born in the places where the universe funnels matter repeatedly and where the supply chain rarely breaks. If you want a monster, you start by choosing an address where the traffic never stops and where the deepest potential well keeps getting deeper. In a node, the universe does not merely place a galaxy. It keeps delivering new material to it, sometimes as intact companions and sometimes as unbound debris. Structure formation is hierarchical, meaning small things form first and later combine into larger ones. In the early universe, small dark matter halos collapse and capture gas because gravity overcomes pressure in dense patches, and cooling allows gas to shed energy. Those halos host the first galaxies, which then orbit, collide, and merge as the web matures, and as larger halos assemble from smaller ones. The large objects we see today are assembled, not simply created in one event, and their present shapes are the sum of many earlier states. Historically, this was a profound shift in how astronomers pictured galaxies. Early debates treated galaxies as more isolated island universes, evolving mostly internally after formation, with environment acting like background scenery. Modern surveys and simulations change that view, revealing that environment and interaction are not side stories, especially in the densest regions. For the most massive galaxies, interaction is the main plot, and isolation is the exception that needs explaining. A merger is not only a collision of stars because stars almost never hit each other. The typical separation between stars is so large that direct impacts are vanishingly rare, even when galaxies overlap in projection. Instead, a merger is a collision of gravitational systems, where orbits are rearranged violently, and the overall potential changes in real time. Energy and angular momentum are redistributed, and the final shape depends on mass ratio, gas content, and orbital geometry, including whether the encounter is head-on or glancing. In visuals, two galaxies approach like ghostly storms, their stars sliding past without contact, while their halos interpenetrate first. Tidal forces stretch each system, pulling out long tails that arc into space, and the tails can carry both stars and gas. The tails are not just pretty, they are evidence of gravity doing work, extracting orbital energy and reshaping the distribution, while also revealing the direction and timing of the encounter. Over time, the tails fade as stars disperse and phase mix into a smoother halo, leaving only subtle asymmetries for careful observers to find. Major mergers happen when two galaxies of comparable mass combine into one. They can transform disks into ellipticals by scrambling ordered rotation and thickening stellar orbits, turning a flat spinning system into a more spheroidal one. They can build central mass quickly, and they can deepen the potential well that binds the remnant, making it harder for later material to escape. If gas is present, they can also trigger starbursts that briefly light up the system, and they can feed the central black hole by driving gas inward. That starburst phase has a physical cause that is easy to picture. Gas clouds collide, shock, and lose angular momentum, so they fall inward rather than staying in stable orbits, and the inflow compresses them further. The central density rises, and star formation can spike for a short cosmic moment, producing bright blue clusters and strong emission lines. Yet in cluster cores, that gas is often missing, and the fireworks are muted because the environment has already stripped or heated much of the fuel. Minor mergers happen when a large galaxy absorbs much smaller satellites. They are more common than major mergers, especially at late times when the biggest systems already dominate and comparable partners are scarce. Each event is modest, but the cumulative effect can be enormous across billions of years because the supply of small companions is large. Minor mergers are the steady diet that can keep a central galaxy growing long after its own star formation slows, and they steadily reshape the outskirts where binding is weakest. A useful way to visualize this is as a slow snowfall of companions. One by one, small galaxies drift in, distort and dissolve, leaving their stars behind as faint additions to the halo. The central galaxy barely flinches at any single impact, yet it changes steadily, because the accreted stars add area more than they add brightness. Over time, the monster is built not by one dramatic feast, but by many quiet meals, each one leaving a thin layer that later blends into the whole. The cluster environment changes the merger story in a specific way that matters for IC 1101. Typical galaxy encounters in clusters are fast, because the velocity dispersion is high, often around 1,000 kilometers per second, and that speed makes capture difficult. Fast flybys do not bind easily, so random mergers between ordinary members are suppressed, even though close passes are common. The center is different, because the most massive satellites lose orbital energy through dynamical friction, and that slow braking can overcome the tendency to simply fly past. Dynamical friction turns motion into heat in the background matter distribution. A massive satellite creates a gravitational wake in dark matter and stars, like a boat raising a trailing swell, and the wake is a real overdensity. The wake is overdense, and its gravity pulls backward on the satellite, acting like a drag force that grows with the satellite's mass. Over many passages, that drag drains orbital energy and shrinks the orbit, and the satellite's path becomes a tightening spiral rather than an endless loop. In a simulation view, the satellite's path spirals inward in slow loops, each one tighter than the last, while the cluster's background responds like a disturbed fluid. The surrounding halo responds, subtly rearranging its own particles as the wake forms and dissolves, and the response is strongest where density is highest. The satellite is not simply falling, it is exchanging momentum with the cluster's background, and the exchange is what makes the center a trap. Eventually, the cluster center becomes a capture zone, and the brightest galaxy becomes the natural endpoint. This is why brightest cluster galaxies keep getting bigger in rich, relaxed clusters. The cluster supplies satellites, and friction delivers the most massive ones to the core, where they are stripped, merged, or both. The process is slow, but it is persistent, and persistence is what matters on cosmic timescales, because even weak effects accumulate. A BCG is less a single galaxy than a long-running accumulation point, and its size reflects the history of the entire cluster. In cluster cores, many mergers are dry, meaning gas poor. The galaxies involved have already lost or consumed much of their cold gas through earlier star formation and environmental stripping, and what remains is often heated or stabilized against collapse. The intracluster medium is hot, often tens of millions of degrees, and it discourages fresh cooling into cold reservoirs because any unfailing gas is quickly heated by shocks. Without cold gas, a merger cannot easily ignite large new star formation, so the light added is mostly old starlight rearranged. The hot intracluster medium is not just hot, it is luminous in X-rays. If we could see in that band, the cluster core would look like a glowing fog filling the space between galaxies, brightest where the gas is densest and pressure is highest. That fog exerts pressure, and it can strip gas from infalling galaxies through ram pressure, like wind tearing leaves from a tree. The result is a population of redder, older galaxies, primed for dry interactions, and the core becomes a place where stellar mass moves around more than it is created. Dry mergers therefore add stars without adding many new stars. They grow the stellar mass by accretion, not by birth, and that distinction shapes the galaxy's appearance, because the stellar populations stay old and metal-rich. They also preserve the old red stellar populations typical of BCGs, because little fresh blue light is created, and dust is scarce. The galaxy can expand dramatically while staying visually mature, and its colour becomes a clue to its growth mode. Dry mergers have a structural signature that matters for IC 1101's extreme scale. They tend to deposit stars at large radii, building diffuse envelopes rather than dense new cores, because incoming material is tidally heated and spread out. The central density changes less than the outskirts, because incoming stars are spread out by tidal forces and by the changing potential during the merger. The effective radius can increase strongly even when the total stellar mass increases more gently, and that is why size alone can mislead. This is where intuition breaks if we equate size with mass too directly. A galaxy can become much larger in radius without becoming proportionally more massive, because radius is sensitive to where stars end up, not just how many exist. If the new stars settle mostly in the halo, the measured boundary moves outward fast, even though the core barely changes. Repeated accretion can move the edge faster than it thickens the center, and the galaxy begins to look like a bright nucleus wrapped in a vast, faint veil. Observers feel this effect in the way surface brightness profiles behave. The inner light may follow one slope, while the outer envelope becomes shallower and more extended, and the transition can be gradual rather than sharp. At large radii, the light is faint, and measuring it requires careful subtraction of background and scattered light, because the sky itself is bright compared to the target. The monster can hide in plain sight, because its outer parts are almost invisible, and the difference between detected and missed can hinge on calibration. Minor mergers are especially efficient at puffing up the outskirts. A small satellite is tidally disrupted, and its stars are deposited on wide orbits that can reach far beyond the original galaxy, because the satellite's binding energy is low. The added material lives in the halo, where surface brightness is low but area is huge, so small additions matter. Over many events, the outer profile becomes extended, and the galaxy's measured diameter inflates, even if its central brightness stays nearly unchanged. In a visual sequence, a satellite approaches, stretches into a ribbon, then dissolves into a faint shell that wraps around the central light. The shell expands and fades, then another arrives, and another, layering the outskirts like rings in a tree, each one marking a different arrival time. None of these layers are crisp forever, because phase mixing smears them into a smooth glow, and the cluster's tides accelerate the blending. Yet the memory remains in the overall structure, and in subtle bumps that deep imaging can still uncover. There is a useful scaling idea that emerges from simulations and observations. If growth is dominated by minor mergers, size can grow faster than mass, sometimes dramatically so, and the relation between radius and mass becomes steeper. The galaxy's outer regions become a repository for accreted debris, while the inner regions remain comparatively stable, because they are already tightly bound. This helps explain extreme radii without requiring extreme recent star formation, and it reframes bigness as redistribution rather than creation. The reason is partly energetic and partly geometric. Low-mass satellites are easier to disrupt, and their stars are deposited where binding energy is low, because the cluster and the central galaxy can unbind them with modest tidal work. Those stars settle into extended orbits, because the merger does not concentrate them into the deepest part of the potential, and because angular momentum is not fully cancelled, the galaxy grows outward like a city adding suburbs, not like a tower adding floors, and the suburbs can spread for hundreds of thousands of light years. In other words, the monster is not built by making stars everywhere. It is built by relocating stars into a larger volume, then adding more stars into the outskirts, where the gravitational grip is weaker. The halo becomes an archive of accretion, and its faintness is part of the physics, because the same light is spread across more sky. The dimness is not failure, it is the signature of assembly, and it is why the largest systems require the deepest observations. But mergers are only one channel for building a giant envelope. The cluster itself strips galaxies, even when they do not fully merge with the central object, and the stripping can be continuous. Tidal forces near the core can peel stars from satellites during close passages, especially from their outer disks and halos. Those stars form streams, shells and plumes before they mix into a smoother glow, and the glow becomes a shared component of the cluster core. Tidal stripping is strongest where the gravitational field changes rapidly with distance. The cluster core provides exactly that steep gradient in the potential, because mass is concentrated and velocities are high, so small changes in position produce large changes in force. A satellite can survive as a bound remnant while losing a large fraction of its outer stars, and repeated passes can whittle it down further. The cluster is not only a merger factory, it is also a stellar shredding machine, and the two processes feed each other. Imagine a small galaxy plunging through the core on a stretched orbit. Its outer stars feel a different pull than its inner stars, and that differential force unbinds them, creating leading and trailing arms. The unbound stars trail behind and ahead, drawing pale arcs that wrap around the centre, and the arcs can intersect to form shells. Over time, those arcs dissolve into a diffuse background that is hard to assign to any one parent, and the core becomes a blended light field. The stripped stars contribute to intracluster light, a diffuse population not bound to any single galaxy. Intracluster light grows as clusters age and as more satellites are processed by tides and harassment, and it can carry a significant fraction of the cluster's total starlight. It is a tracer of cumulative disruption, spread thin across the core like mist, and it often follows the cluster's overall potential. It is also a definitional trap because it overlaps with CD envelopes, and the overlap is strongest where IC1101 lives. Depending on how we define boundaries, intracluster light may be counted as part of IC1101's halo. Photometrically, the light can look continuous from the galaxy outward, with no obvious break, especially when the profile is shallow and extended. Dynamically, many of those stars may orbit the cluster potential rather than the galaxy itself, and their velocities can reflect the cluster's dispersion. The largest galaxy claim can therefore change with the definition used, and the uncertainty is not merely academic. This is not a semantic trick, it is a real, physical ambiguity. In the deepest potential wells, the transition from galaxy to cluster is gradual, not abrupt, and the gravitational influence changes smoothly with radius. The outer stars do not announce which potential they belong to, because gravity does not label ownership, and their orbits can wander. We infer belonging through models, profiles, and kinematic traces when available, and even then the answer can be probabilistic. Kinematics, when we can measure it, becomes the detective's tool. If stellar velocities at large radii match the cluster's dispersion more than the galaxy's, that hints at cluster binding and a shared intracluster component. If they rotate with the galaxy or show a distinct dispersion profile, that hints at galactic binding, even far out. Yet the data are difficult, because the light is so faint where the question matters most, and because foreground stars and background galaxies complicate the measurement. Dark matter makes that ambiguity unavoidable, because it defines the true gravitational domain. Every luminous galaxy sits inside a much larger dark matter halo, and that halo extends far beyond visible stars, often by an order of magnitude in radius. The halo is the main reservoir of mass, and it shapes orbits even where starlight vanishes, setting escape speeds and tidal radii. If we talk about size in a gravitational sense, we must talk about halos, because halos are the real containers of galaxies. The idea of invisible mass has its own history, and it reshaped astronomy in the 20th century. Galaxy rotation curves and cluster dynamics implied far more mass than stars could provide, and the discrepancy persisted across many systems and methods. Later, gravitational lensing offered another way to map that mass without seeing it directly, using the bending of background light as a ruler. In clusters, lensing reveals a deep potential that dwarfs any single galaxy, and it confirms that the monster sits inside an even larger monster. A common theoretical boundary is the virial radius, tied to dynamical equilibrium. It marks the region where the average density exceeds a chosen threshold relative to the universe's critical density, and the threshold is a convention used for consistency. It is not a physical wall, but it is a practical way to define a halo's extent in models, especially in simulations. Within that radius, the system is approximately bound and relaxed in a statistical sense, even though individual orbits can be complex. Even that definition carries subtlety, because halos are not perfectly spherical or perfectly settled. They keep accreting along filaments, and their outskirts can be dynamically young, with subhalos still on first infall. The virial radius is therefore a convention that helps compare systems, not a sharp edge, and different conventions shift it slightly. Still, it provides a language for scale that starlight alone cannot, and it reminds us that the visible galaxy is only the inner trace of a larger structure. For a BCG inside a rich cluster, the situation becomes layered. The galaxy has its own stellar distribution and inner halo, shaped by its merger history and by the way accreted stars are deposited. The cluster has a much larger dark matter halo that dominates at large radii and sets the overall potential, including the motions of intra-cluster stars. IC 1101 sits at the center of that cluster halo, so the galaxy's gravitational story is inseparable from the clusters, and the boundary between them is naturally smeared. This is why largest can refer to different components that do not share one boundary. Largest in starlight depends on surface brightness limits and decomposition choices, where we decide the galaxy ends and where the background begins. Largest in stellar mass depends on population modelling and the assumed initial mass function, which sets how much mass we assign to a given light. Largest in gravitational reach depends on halo definitions, and on whether we mean the galaxy halo or the cluster halo, and those are not the same object. Even the act of measuring starlight has a built-in tension. The outer envelope can sit near the brightness of the night sky background, so small systematics matter, including scattered light from bright stars and subtle gradients in the detector. Different telescopes, filters and reduction pipelines can shift the inferred radius, and the difference can be tens of kiloparsecs. The monster's size can therefore be partly a story about how we see, not only what exists, and that uncertainty is part of the mystery. The growth of dark matter halos is also hierarchical, and it continues even when star formation slows. Halos merge, accrete, and develop substructure, building deep potentials over time, and their mass profiles evolve as material falls in and relaxes. The central galaxy rides inside that evolving potential, responding to it through mergers and tidal interactions, and its stars trace only the inner region. The monster's visible envelope is therefore a luminous skin on a much larger dark framework, and the framework sets the rules. In a wide visual, the stars occupy the center like a bright ember, while the dark matter halo is implied by lensing arcs and simulated density contours. The halo is not an accessory, it is the stage, and the stage is larger than the actors we can see. It dictates how satellites fall in, where they are stripped, and how long they survive, because it sets tidal forces and orbital times. The galaxy's growth is choreographed by an invisible mass distribution, and the choreography is slow enough to look like stillness. The cluster center is special for another reason that shapes IC 1101's history. It contains a vast reservoir of hot intracluster gas that should cool and condense, because it radiates energy away in X-rays, and the densest gas cools fastest. If it cooled efficiently, it would feed star formation and build a brighter, younger central galaxy, potentially creating a blue core. Yet many cluster cores do not show the star formation rates that simple cooling predictions imply, and the missing stars demand an explanation. This mismatch was once called the cooling flow problem, and it forced a rethink of cluster physics. The gas has short cooling times in the core, yet it does not form stars at the expected pace, and the predicted inflows are not seen at the required levels. Something must be reheating it, stirring it, or preventing it from settling into cold clouds, and the mechanism must operate repeatedly. The solution points to the central black hole, not as a minor detail but as a thermostat for the entire core. Feedback provides the missing regulation, and the central black hole is the key actor. As gas accretes onto the black hole, energy is released in jets and outflows that can extend far beyond the galaxy, carrying mechanical power into the surrounding medium. That energy couples to the intracluster medium, heating it and inflating cavities in the X-ray glow, and the cavities can rise like bubbles in a fluid. The heating offsets cooling, preventing runaway condensation and suppressing star formation, while still allowing the galaxy to grow by accretion of stars. In visuals, radiolobes appear like twin shadows carved into the hot gas, aligned with a central engine we cannot see directly, and their edges can be sharp where shocks compress the plasma. X-ray images show bubbles, dark depressions, where the gas has been pushed aside, and bright rims where it is compressed. Around them, ripples and shocks propagate outward, carrying energy into the core, and the ripples suggest repeated outbursts rather than a single event. The cluster is not quiet, it is regulated, and the regulation is written into the gas. This regulation matters because it locks in the dry merger mode of growth. If cooling is throttled, the central galaxy cannot easily grow by forming new stars from fresh cold gas, and any residual star formation remains modest. It grows by absorbing existing stellar systems and by collecting stripped stars that the cluster provides, which naturally builds a diffuse envelope. The galaxy becomes larger and more diffuse without becoming a blue star-forming disk, and its redness becomes a record of suppressed cooling. Feedback also shapes the cluster core's thermodynamics over long timescales. It can maintain a quasi-steady state where gas cools somewhat, then is reheated by intermittent outbursts, and the timing can be irregular. The cycle is not perfectly balanced, because nature rarely is, but it is persistent enough to matter, and it keeps the core from collapsing into a star-forming frenzy. The result is a central environment where mergers continue, while star formation remains limited, and where the monster grows mostly by rearrangement. There is a deeper consequence hidden in that balance. By preventing cold gas from accumulating, feedback changes what kinds of mergers are possible, and it changes how the remnant responds. Gas-rich mergers are rarer, and gas-poor accretion becomes the default, so the galaxy's growth is less dissipative and more kinematic. The monster's growth becomes a story of dynamics and redistribution, rather than a story of new stellar birth, and that story leaves a different structural fingerprint. All of this unfolds on timescales that resist human intuition. Orbits decay over billions of years, not over dramatic moments, and the sky does not show the motion directly because we see only a frozen frame. Streams phase mix slowly, turning sharp features into smooth halos that look deceptively calm, and the calm can be misleading. The largest galaxies are not built in a single era. They are assembled across most of the universe's history, and their present form is a long average of past violence. That long time scale is why the biggest galaxies feel like archives. Each merger adds stars, and it also adds dynamical heating that reshapes the structure and puffs up the distribution, especially in the outskirts. Each stripped satellite contributes to a shared glow that blurs ownership in the cluster core, and the glow can outlast the identifiable streams that created it. The final object is a layered record of many lives absorbed, and the record is written in faint light that demands patience to read. If we linger on the imagery, the core becomes a palimpsest. Faint shells overlap, streams fade into haze, and the central light remains steady as the background changes, as if the galaxy is holding still while history moves around it. The monster looks serene, yet it is the endpoint of countless disruptions, and the serenity is a kind of optical illusion. Calm is what violence looks like after enough time has passed, and after the debris has been smoothed into a glow, yet the story raises a tension that cannot be ignored. If hierarchical growth keeps feeding the center, is there any upper limit, or is the only limit the age of the universe? Does physics impose a maximum size, or can the envelope expand without bound, as long as there are satellites to harvest? At some point, the concept of a single galaxy must compete with the concept of the cluster itself, and the competition is not just philosophical. Several constraints suggest that growth is not infinite, even if it is dramatic. The supply of massive satellites is finite, and it declines as the cluster is processed and its brightest members are already consumed, leaving mostly smaller prey. High velocities limit how often newbound mergers occur outside the friction-dominated core, so the outer cluster becomes a place of flybys rather than captures. The expansion of the universe also reduces fresh infall at late times, especially as dark energy accelerates cosmic expansion and weakens the web's ability to deliver new material. Another limit is practical, but it reflects real dynamics. As stars are deposited farther out, They spend more time in the cluster's overall potential than in the galaxy's inner one, and their orbits become less tied to the central body. The outer envelope becomes less tightly bound to the central galaxy's identity, and more representative of the cluster core as a whole. Growth continues, yet it becomes harder to say what is growing, because the added light belongs to a shared gravitational domain. There is also a definitional limit that becomes a physical one. If the outer stars are mostly intracluster light, then calling them part of the galaxy becomes less meaningful, because their dynamics and spatial distribution follow the cluster. The boundary between galaxy and cluster becomes the real frontier, not a simple radius, and the frontier shifts with how we observe. The monster can grow until it becomes hard to say what it is, and that ambiguity is part of what makes IC 1101 so instructive. IC 1101 sits near that frontier, which is why it is such a useful case. It shows how repeated dry mergers can inflate size faster than mass, producing an enormous effective radius that challenges casual intuition. It shows how stripping can build a diffuse envelope that may be counted differently by different studies, depending on surface brightness limits and modelling choices. It shows how dark matter halos and hot gas regulation set the stage for growth without starbursts, allowing the galaxy to expand while staying old. The central question sharpens as we reach the edge of starlight. How can galaxies and galaxy-scale structures grow so large without breaking intuition? And what does edge even mean when the light fades gradually? What does largest really mean when stars, dark matter, and environment define size differently, and when each definition answers a different physical question? In a cluster core, the universe forces us to answer with more than one number, and to admit that boundaries can be negotiated. We are left with an unsettling observation, one that feels almost philosophical. The more massive the environment, the less clean the boundaries become, and the more galaxy turns into a gradient, fading into a shared background. Perhaps that is the real lesson of monsters like ICLN01. They are not exceptions to the rules, they are the rules written in extreme ink where the usual categories begin to blur. To find the limits, we must expand the definition of galactic structure beyond starlight into radio lobes and jets that rewrite what size can mean. To find the limits, we expand the definition of galactic structure beyond starlight into jets and lobes that redraw what size can mean. IC 1101 taught us that edges blur when stars fade into intracluster light, and when ownership becomes a matter of thresholds. Radio galaxies push that ambiguity further, because their largest structures are not stars at all. They are plasma, magnetic fields, and radiation, stretched across intergalactic space by a central engine. In the optical, the host can look like a normal elliptical smudge, but radio maps reveal a second body, vast, bilateral, and faint. The contrast can feel like a trick of perspective, yet it is simply a reminder that the universe has more than one kind of glow. A radio galaxy begins with a supermassive black hole in a galactic nucleus, typically millions to billions of solar masses. Gas and dust fall inward, forming an accretion disk that heats as it spirals down. Friction and magnetic turbulence convert gravitational potential energy into heat, so the inner disk can glow in ultraviolet and X-rays. In that inner region, temperatures rise high enough that atoms cannot stay intact, and matter becomes an ionized plasma. The disk is not just a furnace, it is a generator for ordered magnetic fields. Fields that can organize chaos into direction. Those fields twist and tighten as the disk rotates, because conducting plasma drags magnetic lines along with it. In the language of magnetohydrodynamics, the disk behaves like a dynamo, amplifying and ordering fields through shear and turbulence. Under the right conditions, the field lines thread the inner disk and the region near the black hole, then rise like taut cords. They can tap the energy of the spinning disk and the black hole itself, then channel it outward. The result is a pair of jets that emerge along the system's rotation axis, as if the galaxy has found a preferred direction in space. Even the word axis matters here, because it implies persistence, an orientation that can survive for millions of years. The crucial correction is simple and non-negotiable. Matter does not shoot out from inside the event horizon, because nothing escapes that boundary. The jets are launched from the accretion flow and magnetized regions just outside the horizon, where plasma is still part of the observable universe. The launch zone is small in absolute terms, measured in a few gravitational radii, yet it controls a structure that can cross megaparsecs. This matters because it keeps the story physical rather than mythical. No violation is required, only extreme conditions. In accessible terms, the black hole is not a cannon. It is the anchor for an extreme electromagnetic machine, fed by infalling material. The energy comes from gravity and rotation, then leaves as collimated outflow. Some of that energy is carried as bulk motion of plasma, and some is carried as electromagnetic energy in the fields themselves. In many models, the early jet is Poynting flux dominated, meaning the fields carry the power before particles take over downstream. The jet is less like a stream of bullets, and more like a structured flow, where fields and particles travel together. If you could slow time and trace it, you would see a conduit that is both matter and geometry. Visually, the scene is not a fiery eruption you could watch with your eyes. Imagine a dark nucleus wrapped in a bright inner disk, with invisible lines of force twisting upward into two narrow funnels. The funnels pierce the host galaxy's halo, then continue into the thin outskirts where starlight is scarce. Dust lanes and old stars might frame the center, but the true action is offstage in wavelengths we cannot see. On a radio image, those funnels become luminous threads, and the emptiness around them becomes part of the composition. The galaxy's visible body looks self-contained, while its radio body looks like a long exhale. The signature that names these objects is synchrotron radiation. Electrons moving near light speeds spiral around magnetic field lines, emitting radio waves as they curve. Because the electrons are relativistic, the radiation is beamed and broadband, spreading from radio up into higher frequencies in some cases. The spectrum is not arbitrary, because it encodes the energy distribution of the electrons and the strength of the magnetic field. Radio surveys see the glow of that motion, even when the host galaxy looks ordinary. In many sources, polarization measurements also betray the geometry of the fields, an invisible structure made visible by orientation. Faraday rotation, where intervening plasma twists the polarization angle, can even hint at magnetized gas along the line of sight. In many systems, the radio emission is not confined to the nucleus. It extends into two lobes, inflated where jets dump energy into the surrounding medium. The lobes can dwarf the visible galaxy, making the radio structure the dominant footprint. If you overlay optical and radio images, the starlight sits like a seed at the center of an enormous, faint double cloud. The galaxy's body becomes a question of which map you trust. The radio map, in effect, is a map of work done, energy deposited into space and left there as a trace. This introduces a parallel category of largest. A galaxy can be modest in starlight, yet enormous in radio extent, because the jets carry influence outward. The question becomes whether size should mean where stars live, or where energy reaches. It is an uncomfortable question because it turns a familiar ranking into a debate about what counts as substance. When you call a lobe part of the galaxy, you're also admitting that a galaxy can extend beyond what is gravitationally bound in the usual sense. Jets remain narrow over distances that feel impossible, and the word impossible is doing real work here. They travel hundreds of thousands, then millions of light years without dissolving into turbulence. Their persistence is a physics problem, not a poetic one. Every meter of that journey is an opportunity for instabilities to grow, yet the structure often holds. The jet boundary is a battleground between ordered flow and mixing, and the fact that order wins so often is itself a clue. Collimation begins near the launch region, where magnetic fields act like rails. A helical field can confine the flow, resisting sideways expansion through magnetic tension. The jet behaves less like smoke, and more like a guided beam, because the field lines supply an internal architecture. In many models, the jet starts magnetically dominated, then gradually converts field energy into particle energy as it propagates outward. That conversion can leave signatures in brightness and polarization, like a change in texture along the beam. Pressure balance matters as the jet moves outward, because it is never traveling through a vacuum. If the surrounding medium is dense and turbulent, it can disrupt the flow and slow expansion. If the environment is thin, the jet can stay coherent longer and inflate larger lobes. Even small differences in external density can accumulate over millions of years, turning modest jets into giant structures. The jet is therefore not only a product of the black hole, but a negotiation with whatever space happens to be nearby. The lobes are not empty balloons, even when they look like faint fog on a map. They are reservoirs of relativistic particles and magnetic fields, mixed with shocked material from the intergalactic medium. Their edges can mark shocks where the jet's energy is thermalized, compressing gas and accelerating fresh electrons. In some sources, bright hotspots appear at the lobe tips, compact regions where the jet slams into the external medium and does its most visible work. Those hotspots can act like signposts, telling us where the jet is currently spending its momentum. Over time, lobes expand and rise through their environment. Buoyancy can lift older plasma away from the host, while new outbursts refill the channel. The structure becomes a time record, layered by episodes of activity. In a deep image, you can sometimes see the outer lobes as a faded envelope, with a younger, brighter pair nested inside, like tree rings written in radiolight. The nested geometry can feel eerily deliberate, yet it is simply the consequence of repeated feeding and repeated outflow. Historically, radio galaxies entered astronomy as surprises because early radio maps did not match optical expectations. In the mid-20th century, radio astronomers found bright sources with no obvious stellar counterpart, and the sky gained a second geography. The early catalogues, built from crude positions and large beams, were full of mysteries that looked like errors. As identification improved, it became clear that some radio sources were galaxies with jets, and that the radio emission could extend far beyond the visible host. The discovery forced astronomers to treat galaxies as multi-wavelength objects, where the most important structures might be invisible to the eye. It also forced a conceptual shift because galaxy stopped being synonymous with what a telescope shows in visible light. For decades, giant radio galaxies were treated as rare outliers. Part of that rarity was physical, because not every black hole launches long-lived jets. Jet production depends on accretion state, magnetic flux near the black hole, and the broader supply of gas. Part of it was observational, because the biggest lobes are faint and easy to miss. The category was shaped as much by our instruments as by nature. In practice, a giant can be created by persistence and sensitivity as much as by raw power. Diffuse radio emission has low surface brightness, and it fades as electrons lose energy. Older lobes can become ghostly, especially at high frequencies where radiative losses bite hardest. Synchrotron losses drain the highest energy electrons first, so the spectrum steepens with age. That steepening is a kind of clock, because it tells us how long the plasma has been radiating since it was last energized. A survey can detect the bright core and miss the true scale, which means the catalogued size can be a lower limit. In the quietest giants, what we fail to see can be larger than what we do. Detection also depends on angular resolution and sensitivity to extended structures. Interferometers can resolve out large, smooth emission if the array lacks short baselines, because the instrument is blind to very broad features. A galaxy can be giant in reality and small in a catalogue, not because the lobes are absent, but because the observing setup filters them away. This is one reason the history of giant radio galaxies tracks the history of radio instrumentation. The sky did not suddenly grow lobes, but our ability to register faint gradients improved. That census changed with new radio arrays and systematic surveys. Instruments designed for wide fields and low frequencies became better at finding aged synchrotron plasma. Low-frequency observations are especially powerful because older electron populations still radiate there, even after they fade at higher frequencies. The sky began to reveal structures that earlier maps filtered away, and the giants stopped looking like unicorns. With each new survey pass, the radio universe feels less like a set of points and more like a faint connected weather map. As the sample grew, the category of giant radio galaxies became less exotic. The distribution extended toward larger sizes, and the tail became harder to dismiss as statistical noise. The universe was not making more giants. We were finally seeing them. Each new detection carried the same quiet implication. There may be more structure hiding below our thresholds. The word threshold becomes a theme, because it is both a technical limit and a philosophical one. Then a modern benchmark arrived with a name that sounded mythic. Alcyonius entered the literature as an extreme case of jet-driven extent. It forced a new calibration of what giant could plausibly mean. In visuals, it reads like a delicate, symmetric stain across the sky, with a small galaxy pinned at the center like a tack. The lobes are so extended that the host seems almost incidental, as if the map were about space itself rather than the galaxy. The measurement is conceptually straightforward, even if the data work is not. Astronomers measure the angular separation between the outer radio lobes on the sky, then correct for projection and identification uncertainties. They combine that angle with the distance inferred from redshift to get a physical size. The method sounds simple, yet it depends on careful mapping of faint edges, where noise and background sources can confuse the boundary. It also depends on deciding which faint emission belongs to the lobes and which belongs to unrelated sources scattered along the same line of sight. The conversion depends on cosmology, because distance in an expanding universe is not one number. Astronomers must choose a cosmological model to translate redshift into an angular diameter distance, and that distance changes with the universe's expansion history. Yet the conclusion remains robust across reasonable parameters. The lobes span millions of light-years, far beyond any stellar halo. Even generous uncertainties do not shrink the structure into anything familiar. At those scales, the radio galaxy stops feeling like an object and starts feeling like a coordinate system. Alcyonius also highlighted the role of environment. A low-density intergalactic medium offers less resistance, letting lobes expand farther before stalling. In a cosmic void or near-void region, the same jet power can paint a larger canvas. The lobes do not need to be stronger than their cousins in clusters, only less confined. It is a reminder that largest can be an environmental achievement, not just an internal one. This is where the story turns eerie rather than loud. The engine can be steady, not explosive, and still reshape space on vast scales. Over millions of years, a persistent jet can do what a brief flare cannot. The power is not a single dramatic moment, but a long, disciplined push that slowly redraws the surrounding medium. If you could watch it in accelerated time, the lobes would swell like slow ink dispersing through water. Except the ink is magnetized plasma. Jet power is often expressed in watts or ergs per second, numbers that do not land emotionally. A better translation is sustained output over deep time, comparable to many supernovae spread across a million years. Another translation is mechanical work done on a thin gas, like a piston that never stops moving. The effect is cumulative, like pressure applied without pause. In that accumulation, the jets become a kind of cosmic weather system, shaping conditions rather than scenery. The weather is invisible in daylight, yet it leaves a measurable climate behind. The jet does not need to roar in visible light. It can be mechanically dominant while the host galaxy looks quiet and red, with little sign of star formation. The most dramatic action can be happening in a band our eyes never evolved to see. That mismatch between appearance and influence is part of the mystery, because it makes the universe feel more secretive than violent. It also invites a question. How many quiet galaxies are quietly doing this in frequencies we have not yet mapped deeply enough? Alcyonius set a new reference point, but it did not end the climb. Another discovery arrived with a span that sounded like a mistake, the kind of number you double-check before you believe it. Porphyrion pushed the category into a scale that collides with how we picture cosmic structure. It was not merely bigger, it was big enough to challenge the mental boxes we use for galaxies. The name feels ancient, and the structure feels ancient too, like a fossil of long-lived activity preserved in radio light. Porphyrion's headline size is about 23 million light-years across. That number is not the diameter of a stellar system, and it is not a cluster radius. It is the separation between radio lobes inflated by one galaxy's central engine. The host galaxy sits at the center like a punctuation mark, while the lobes stretch outward like parentheses enclosing a region of space. In a wide-field rendering, the lobes can look like faint wings, and the galaxy like a pin holding them in place. The conceptual shock is not just the number, it is the comparison. Cosmic voids span tens of millions of light-years, with radii that define the emptiest regions of the web. Porphyrion's jets reach across roughly 2/3 of a void's radius. When you place shocks and seed magnetic fields across large volumes. They can heat tenuous material and alter how it later cools and collapses. In that sense, they participate in structure formation's later chapters, not by building the web, but by editing the conditions inside it. A lobe can be a quiet intervention, changing the temperature and magnetization of a region that would otherwise evolve differently. The edit may be subtle, but across millions of light years, subtle becomes consequential. The persistence problem becomes sharper at these scales. A jet must remain coherent against instabilities that should shred it, including kink modes in magnetized plasma and shear-driven disruptions at its boundary. The fact that we see long, narrow jets implies stabilizing conditions and continuous energy supply. It also implies that the jet is not a one-time launch, but a maintained flow, refreshed faster than it can unravel. The symmetry is therefore not just aesthetic, it is diagnostic, evidence that the engine kept its aim. Magnetic collimation is one stabilizer, especially if the jet carries a strong toroidal component. External pressure from the surrounding medium can also confine the flow, preventing rapid sideways expansion. The jet survives as a balance, not as an invulnerable spear. If either side of that balance changes, the morphology changes too, and the radio sky records the difference. A bend, a flare, or a sudden widening can be read as a change in environment, like wind shaping a plume. The environment shapes that balance, and giant radio galaxies often live where the medium is thin. Lower density reduces entrainment, meaning less external material mixes into the jet and slows it. The jet stays lighter, faster, and more stable. In denser environments, the jet can decelerate, flare, and deposit its energy closer to home, which produces a different kind of radio galaxy. The same central engine can therefore write very different signatures, depending on what kind of paper the universe provides. At the lobe edges, the physics shifts from guidance to inflation. The jet terminates in a hotspot or a working surface, where kinetic energy converts into heat and particle acceleration. The lobe grows as that energy accumulates, pushing against the external medium like a slowly expanding bubble. Over time, the lobe can develop internal structure, filaments, brightness gradients, and polarized arcs that trace the underlying fields. In the best images, those filaments look like smoke, but their motion is governed by magnetism and shock physics. Over time, radiative losses dim the oldest plasma. Electrons lose energy through synchrotron emission and inverse Compton scattering off the cosmic microwave background, which becomes a more severe drain at higher redshift. Inverse Compton losses are especially insidious because they steal energy without producing radio photons, shifting it into higher energy radiation. Low-frequency observations become essential because they catch the aged electrons that high frequencies miss. The giants are often old, and old things are faint. Their faintness is not a flaw in the story, it is the story, evidence of time passing in a medium that barely leaves footprints. This is why recent discoveries cluster around new survey capabilities. Better sensitivity to low surface brightness and better coverage at low frequencies reveal structures that were always there. Improved imaging techniques also help, because separating faint diffuse emission from background confusion is as much an analysis challenge as an engineering one. The universe did not change, our filters did. Each new filter makes the sky feel larger. Each new map quietly suggests that our previous maps were only sketches. There is also a selection effect that hides the larger systems. The bigger the lobe, the fainter its surface brightness tends to be, because the same energy is spread over more area. The giants can be the hardest to recognize, even when they are the most extreme. A catalogue built from bright, compact features will naturally undercount the quietest, widest structures. In that sense, the largest objects can be the most easily overlooked, because they refuse to stand out. So the modern census is still incomplete. Every new survey expands the tail, and every expansion raises the same question. Are we seeing the true maximum, or only the current limit of our detection? The unsettling possibility is that largest known is a statement about us, not about nature. If the boundary keeps moving with our instruments, then the boundary was never a wall. It was a sensitivity curve. The stakes rise because these structures complicate the film's central question. We asked how galaxies and galaxy-scale structures grow so large, and what largest really means. Giant radio galaxies answer by changing what counts as a galaxy's body. They suggest that a galaxy can have an extended presence without extended starlight, and that influence can be mapped as geometry rather than mass. The map is thin and faint, yet it is still a physical imprint, an energetic signature written into the medium between galaxies. If we crown largest by starlight, IC 1101 remains a contender through its halo and envelope. If we crown largest by energetic reach, a radio galaxy can dwarf any stellar system. The competition becomes a debate about categories, not just numbers. That debate is not pedantic because categories determine what we measure, and measurement determines what we think the universe is doing. When a category changes, the universe does not change, but our interpretation of its architecture does. Yet the categories are not arbitrary. Stars trace where baryons settled into long-lived orbits, shaped by mergers and dark matter. Jets trace where a black hole can deliver energy, shaped by magnetic fields and environment. One is a record of assembly, the other is a record of activity. Both are rooted in physics, and both leave signatures that can persist long after the initiating events. The persistence is different in kind. Mass can remain while radiation fades, and a faint radio lobe can vanish from view without ever having been unreal. Both are physical, and both matter for cosmic evolution. One is a map of assembled matter, and the other is a map of injected energy. The universe contains multiple ways for bigness to exist, and they do not align. When they disagree, the disagreement is telling us something about how galaxies connect to their surroundings. It may also be telling us that galaxy is not a single object, but a system with multiple outward-facing interfaces. This is why the comparison feels unsettling. A galaxy's stellar halo grows by collecting and mixing, and its boundary blurs into a cluster. A galaxy's radio lobes grow by pushing outward, and their boundary blurs into intergalactic space. One boundary is a fading density of stars, while the other boundary is a fading brightness of synchrotron emission, and both depend on where we draw a line. In both cases, the edge is not a place you can point to, but a region where the signal gradually gives up. In both cases, the edge is not a wall. It is a gradient where definitions and detection thresholds decide what we call real. The difference is that radio lobes can cross regions where there are almost no stars to confuse the story. The emptiness makes the structure feel more audacious, because it occupies a volume that looks, at first glance, like it should belong to nothing. Yet the radio glow insists that the volume has been touched, organized, and energized. That emptiness makes the lobes feel like an intrusion into the cosmic web. They occupy volumes that would otherwise be quiet, and they do so with a geometry that points back to one nucleus. The structure is a line drawn across the universe. In a wide-field visualization, the lobes resemble faint brushstrokes laid over the dark, filamentary background of large-scale structure. The brushstrokes are not random, and their symmetry is what makes them feel almost intentional. The calm tone matters here, because the engine is not cinematic in the usual way. It does not explode once and vanish. It persists and repeats. It reshapes space through patience, like erosion working in reverse. The longer you stare at the map, the stranger it becomes that such a small origin can maintain such a large symmetry. The symmetry is a kind of long-distance whisper, carried through plasma that barely exists by everyday standards. If Porphyrion can span void-like scales, the idea of a galaxy's influence becomes elastic. Influence can mean gravity, which is dominated by dark matter halos and clusters. Influence can also mean feedback, which can travel far beyond the mass distribution. When we say a galaxy is large, we may be revealing which kind of influence we instinctively respect. Do we privilege what holds matter together, or what can reach outward and alter conditions? This is where earlier chapters echo in a new register. We saw how cluster environments blur the boundary between galaxy and cluster light. Now we see how black hole activity can blur the boundary between galaxy and the intergalactic medium. In one case, the blur comes from stars stripped and shared. In the other, the blur comes from energy exported and dispersed. Both blurs are real, and both are reminders that the universe does not label its own components for our convenience. The central engine is tiny compared to the structure it creates. The event horizon is smaller than our solar system, yet the jets can span millions of light years. The mismatch is the point, because it breaks intuitive scaling. It suggests that in astrophysics, leverage matters as much as size, and that a compact object can act as a long-range agent. The black hole is small, but the physics near it is extreme enough to matter far away. It also reframes what a galaxy can do. A galaxy is not only a collection of stars bound by gravity. It can be the launch site of structures that are not bound in the same way, yet remain causally connected to the nucleus. The connection is not a rigid rod, but a continuous supply of energy and plasma that keeps the alignment meaningful. When the supply stops, the geometry remains for a while, then fades like a contrail in a thin sky. The causality is visible in symmetry and alignment. Two lobes on opposite sides point to a common origin and a common axis. Even after millions of years, the geometry preserves the memory of the central spin. That memory is fragile, which makes its survival informative, because it implies stability in the orientation of the inner engine over long periods. If the axis wandered wildly, the lobes would look like a smear rather than a clean bilateral form. That memory can survive multiple outbursts. Some radio galaxies show restarted activity, with inner lobes nested inside older outer lobes. The structure becomes a stratigraphy of black hole feeding cycles. Each cycle leaves a partial imprint, and the combined imprint becomes a history written across intergalactic space. In that history, silence matters as much as activity, because gaps can mark times when the engine starved. Feeding cycles connect back to the cluster thermostat we discussed earlier. In dense environments, jets can carve cavities in hot gas and regulate cooling, preventing runaway star formation. In low-density environments, jets can run farther before they deposit energy, building giants. The same physical mechanism can either heat a cluster core or sketch a megastructure across a near void, depending on what surrounds it. Context decides whether feedback looks like local maintenance or long-distance reach, so the same mechanism produces different largest outcomes depending on context. Dense gas confines and brightens the interaction near the core. Thin gas allows expansion and faintness, trading brightness for reach. A radio galaxy can therefore be judged by two different spectacles, one that favours dramatic hotspots and one that favours ghostly extended lobes. The giants tend to belong to the second spectacle, where the drama is spread thin across enormous space. This helps explain why the most extreme giants are not always in the richest clusters. They can thrive where the intergalactic medium offers little resistance. The biggest radio structures may prefer cosmic outskirts, not cosmic cities. The outskirts are quieter, but they are also more permissive, and permissive environments can produce the longest signatures. The quietness is not emptiness, but low pressure, and low pressure is an invitation to expand. The implication is unsettling for our ranking instincts. The largest galaxy in starlight may live in a cluster core, swollen by mergers and intra-cluster light. The largest galaxy in radio may live in relative emptiness, swollen by unimpeded lobes. Two different kinds of largeness point to two different kinds of cosmic neighbourhood. The universe, in effect, offers two different arenas, and the champions do not have to compete on the same field. So we return to the definitional trap with higher stakes. Are we measuring the wrong thing when we crown a largest galaxy? Or are we discovering that largest is not a single contest, because the universe offers multiple scoreboards? The deeper question is whether the scoreboards reflect different physical roles, matter assembled versus energy delivered. If so, then arguing about one largest may be like arguing about whether a storm is defined by wind speed or by rainfall. The tension is productive because it forces a new comparison. IC 1101's halo is matter assembled and held, blurred by a cluster's gravity. Giant radio lobes are energy delivered and dispersed, blurred by the thinness of intergalactic space. Both can reach millions of light years, yet they mean different physics. One is a boundary of binding and membership, the other is a boundary of influence and interaction. Both boundaries are real, and both are conditional, and neither boundary is final, because both depend on time. Stellar halos grow as mergers continue and as stripping adds intracluster light. Radio lobes grow as jets persist, then fade as electrons cool and fields relax. A radio giant can be enormous for a window of cosmic time, then become invisible at common frequencies, leaving only a subtle imprint in the lowest bands. The structure can still exist as aged plasma, yet it can slip below our practical definition of there. So the largest structure is also a question about when we look. A stellar halo can be permanent in mass, yet ambiguous in ownership. A radio halo can be unambiguous in geometry, yet temporary in visibility. The universe keeps reminding us that size is not only spatial, but temporal, and that detection is part of the definition. The map we draw is always a collaboration between nature and our ability to register faint signals. This chapter's lesson is not that one category wins, it is that the universe refuses to give us one definition of size. It offers size in stars, size in dark matter, and size in feedback, each with different edges. When those edges disagree, the disagreement is not a flaw, it is a clue. The clue is that galaxies are not sealed islands, and their boundaries are negotiated with their environments. We end with the core question sharpened rather than answered. If a single black hole can draw a structure across void-like distances, what boundary is nature actually enforcing? And if boundaries depend on definition, what does it mean to call anything the largest? The radio sky suggests that the universe's limits may be less about walls and more about conditions. Conditions decide whether a jet survives, whether a lobe expands, and whether a faint edge remains visible long enough to be counted. Next, we return to IC 1101 with this new yardstick in mind, comparing a stellar empire to a jet-defined megastructure, and asking whether any limit is physical at all. We return to IC 1101 with a new yardstick, and the yardstick immediately splits. Largest can mean the widest starlight, the biggest effective radius, the farthest halo, or the broadest gravitational domain. It can also mean the farthest reach of jets, or the widest glow of a cluster's shared light. The central question sharpens here. How can galaxies grow so large, and what does largest mean when size has multiple definitions? Begin with the simplest metric, because it feels intuitive when you first see a galaxy image. Diameter of the luminous body depends on where we stop counting photons, and that stopping point is never purely natural. Observers pick an isophote, a surface brightness threshold, and call that contour an edge. On screen, that edge looks like a clean outline, yet it is really a statistical decision made under imperfect sky conditions. Change the threshold and the edge moves, because the outskirts fade gradually rather than ending. A galaxy's light profile is more like fog thinning into night than a coin cut from paper. In a deep optical frame, the centre of IC 1101 is almost overconfident, bright, smooth, and apparently self-contained. Then the glow loosens, and the galaxy becomes a gradient, a pale wash that refuses to stop on cue. If we could lower the brightness slider in real time, the edge would breathe outward with every adjustment. That breathing is not the galaxy changing, it is us changing the rules of what counts as visible structure. Surface brightness is measured in magnitudes per square arc second, which is a way of describing faintness per unit area. That unit matters, because a huge diffuse envelope can hide in plain sight while still containing enormous total light. A bright core can dominate a casual image, even when a vast halo holds a comparable fraction of the stars. When astronomers push to extreme depths, they are not just collecting more photons. They are fighting the sky itself, airglow, scattered moonlight, and subtle gradients that drift across the detector. Even in space, zodiacal light from interplanetary dust adds a smooth glow that must be modelled and removed. What looks like empty blackness in a finished picture is actually a complicated foreground. Earth's upper atmosphere flickers with emission lines that change over minutes, and those changes imprint gentle bands across exposures. Dust in our own galaxy can reflect starlight into faint filamentary cirrus that masquerades as extragalactic haze. Even the optics contribute, because internal reflections and ghosting concede broad, low-contrast patterns. At the level where CD envelopes live, the background is not background. It is a competing signal that must be understood, not merely subtracted. Cosmological surface brightness dimming makes the same physical halo harder to see at greater distance. The effect scales steeply with redshift, so a distant giant can look deceptively compact. A deep exposure does not fully solve this, because the dimming is built into the geometry of an expanding universe. Photons arrive stretched in wavelength and diluted across a larger apparent area, and the penalty compounds. So, largest by starlight is partly a statement about depth, calibration, and the chosen cutoff. It is also a statement about patience, because the faintest outskirts require long integrations and careful control of systematics. Historically, this problem has shadows. Early photographic plates could capture bright bulges and disks, yet they struggled with the low surface brightness outskirts. The emulsions had limited dynamic range, and the chemical development process introduced its own nonlinearities. As detectors improved, galaxies seemed to grow new limbs, halos, shells, and envelopes that older instruments simply could not hold. The record books changed, not because galaxies changed, but because our eyes did. IC 1101 sits in that tradition, a modern test of how far we can trust the faintest light. There is a quiet historical irony here. In the mid-20th century, astronomers debated whether the faint outskirts were real structure or photographic artifact. Today the debate continues with different tools, flat fields, scattered light models, and PSF characterization, but the same unease. Every generation redraws the boundary of a galaxy with the best available technology. That makes largest feel like a moving target because in a sense it is. A second metric sounds more objective because it compresses a complex profile into a single radius. The effective radius is the radius enclosing half the total light. It is often called Re, and it anchors scaling relations used across extragalactic astronomy. Those relations connect size, brightness, and stellar velocity dispersion, and they hint at how galaxies assembled. Yet total light depends on how far the profile is integrated, and on how the sky background is removed. A tiny error in the background can shift the integrated light enough to move the half-light point dramatically. This sensitivity is easy to underestimate. If the outer profile is shallow, then a small change in the assumed sky level adds or removes a large area of faint flux. That extra flux barely changes the image by eye, yet it can change the cumulative light curve by a lot. The half-light radius then slides outward, as though the galaxy has expanded. So Re is not just a property of the galaxy, it is also a property of the measurement choices that define total. In CD galaxies, the outer envelope can dominate the integral, inflating effective radius dramatically. That envelope is not a simple extension of the inner galaxy. It can carry the signatures of repeated accretion, stars deposited on wide orbits by disrupted satellites. In images, the inner regions may look like a classic elliptical, smooth and bright. Farther out, the light becomes an almost imperceptible glaze, spread across tens or hundreds of kiloparsecs. The physics behind that glaze is slow and cumulative. A satellite falls in, tides peel off its outer stars, and those stars settle into the host's outskirts. Over many events, the envelope becomes a layered archive, mixing debris from different directions and different epochs. Some of that debris remains in coherent streams for a while, like faint brushstrokes around the main body. Given enough time, orbital precession and phase mixing smear the brushstrokes into a smooth wash. The result looks serene, but it is built from repeated disruption. Different profile fits can split the light into components, and the split changes the half-light radius. A single Circic profile may force the outskirts to follow the inner shape, even if the physics differs. A multi-component fit can assign one part to a central elliptical and another to an extended CD envelope. Neither approach is automatically true, because both are models applied to noisy systematics limited data, so effective radius can reorder the list, promoting diffuse giants over compact but massive ellipticals. This is where the language of component becomes slippery. A fitting function can create the illusion of distinct structures, even when the real galaxy is a continuum. Conversely, a single function can hide a genuine transition because it is forced to compromise. The fit is a tool, not a verdict. In the most extreme systems, the tool can decide the ranking. A third metric pushes outward, toward the region where a galaxy becomes a hypothesis. The stellar halo extent asks how far bound stars plausibly reach. In practice, we infer it from faint photometry, sparse traces, and models of the potential. Traces can include globular clusters, planetary nebulae, and satellite galaxies whose motions map the mass distribution. Each tracer has its own biases, and each samples a different part of the gravitational field. Globular clusters are especially useful because they are bright, compact, and numerous around massive galaxies. Their colours can separate metal-rich populations tied to the central body from metal-poor populations linked to accretion. Planetary nebulae, with their sharp emission lines, can be detected where the continuum starlight disappears. Satellites provide a different handle, because their velocities respond to the total mass on large scales. Yet satellites are not test particles. They have their own histories, and their orbits may not sample the halo evenly. At the radii that matter, the light is comparable to background systematics, not to detector noise. That distinction is crucial, because random noise averages down with more exposure time. Systematics do not average down so easily, because they are built into optics, calibration, and sky modelling. Flat field errors, scattered light, and the telescope's PSF wings can mimic or erase a faint envelope. The PSF wings matter because bright inner light can be redistributed outward, creating a false halo. The PSF is not just a sharp core. It has extended wings produced by diffraction, micro roughness on mirrors, and scattering inside the instrument. A tiny fraction of the central light, spread over a huge area, can rival the brightness of a real CD envelope. If that wing is not modelled correctly, the outskirts become a mirage. Deep imaging teams therefore measure the PSF using bright stars, then propagate it into their galaxy models. The process is painstaking because the error budget lives in the details. Sky subtraction becomes the decisive step, and different pipelines can move the claimed boundary by huge amounts. A pipeline that assumes the background is smooth may subtract away real diffuse structure. A pipeline that preserves large-scale gradients may mistake instrumental patterns for galaxy light. This is why deep imaging papers often devote as much space to reduction strategy as to astrophysical interpretation. When the signal is a whisper, the method becomes part of the measurement. This is the core ambiguity. Where does IC or 1101 end when its envelope blends into intra-cluster light? In Able 2029, the cluster core is filled with stars that were stripped from many galaxies. Those stars can form a smooth glow that follows the cluster potential more than any single galaxy. Visually, it can look like a pale tide pool of starlight, filling the space between brighter islands. On a wide shot, the cluster center feels like a layered scene. Bright ellipticals sit like stones in shallow water, while a diffuse sheen fills the gaps between them. The sheen is not uniform because the cluster is not static. It can show fainter symmetries, subtle plumes, and long arcs that hint at recent interactions. But at typical depths, those hints blur into a continuous glow. That continuity is what makes ownership difficult. Intra-cluster light is not merely a nuisance. It is a fossil record of interactions, harassment, tidal stripping, and the slow grinding of orbits in a dense environment. Simulations show that as clusters assemble, they shed stars into a shared component. Those stars can carry information about when the cluster formed and how violently it evolved. Some were stripped early, when the cluster was still assembling from groups. Others were stripped late, during close passages near the center. So when we argue about whether the light belongs to IC 1101, we are really arguing about the cluster's history. Photometrically, the transition can look continuous, with no obvious break to declare ownership. A human eye wants a boundary, but the profile may only curve gently, never snapping into a new regime. Dynamically, many of those stars may orbit the cluster, not IC 1101, even if they sit near it. Their velocities can be higher, their orbits less centered, and their phase space distribution more like the cluster than the galaxy. So the edge is not a line. It is a region where membership becomes probabilistic. That probabilistic language matters because gravity does not label particles. A star can pass near the galaxy for billions of years, yet remain energetically tied to the cluster. Another star can wander far out, yet still be bound to the galaxy's potential. If we could plot their velocities against radius, the populations would overlap. The separation becomes a statistical inference, not a visual classification. In that sense, the boundary is an argument in phase space. Intra-cluster light complicates every ranking, especially for central dominant galaxies. Count the shared glow as part of the galaxy, and the largest objects become cluster centers. Exclude it, and the same systems shrink, sometimes by factors that change the record book. The problem is not cosmetic. It reveals that the galaxy and the cluster core are coupled systems. IC 1101 is a lesson in that coupling, because it sits where the boundary is physically blurred. A fourth metric steps beyond stars. Halo extent in dark matter is inferred, not photographed. Here the common language is the virial radius, defined by an overdensity threshold in a cosmological model. The threshold is conventional, so the radius is a practical boundary, not a physical wall. Still, it tracks a real idea. Inside that scale, the system is largely bound and dynamically processed, even if the edge is fuzzy. The virial concept has a history that reaches back to the virial theorem, linking kinetic and potential energy in equilibrium systems. In a cosmological context, the virial radius marks where a halo has roughly settled from the Hubble flow into a bound structure. But halos keep accreting, and their outskirts are not fully relaxed. They contain streams, subhalos, and material on first infall, so the virial radius is a convention that captures a transition, not a cliff. In simulations, the outer halo is a busy place. Matter arrives along filaments, and it does not instantly thermalize into a smooth distribution. Subhalos survive as lumpy structure, and their orbits can carry them deep into the potential. The edge can also depend on which overdensity definition is used, because different communities adopt different thresholds. That is why virial radii quoted in papers can differ even for the same underlying halo. The number is meaningful, but it is not sacred. By this metric, the largest galaxy can become the largest halo, and halos reorder the list again. A galaxy with modest starlight can sit in a huge halo, while a luminous giant can sit in a smaller one. This is why gravitational lensing, satellite kinematics, and X-ray gas profiles matter. They reveal mass where starlight is silent. In clusters, the hot intracluster medium glows in X-rays, tracing the deeper potential that stars alone cannot map. X-ray images add a different kind of visual. Instead of sharp galaxies on black, we see a soft extended cloud, brightest at the center and fading outward. That cloud is plasma at tens of millions of degrees, and it shines through thermal bremsstrahlung and line emission. Its shape responds to gravity, so it outlines the potential well. If the gas is disturbed, it can show ripples, cavities, and cold fronts. Those features hint at feedback and mergers, and they complicate the idea of equilibrium. Even virial language becomes tricky at a cluster center. IC 1101 has a galaxy-scale halo, but it also sits inside the far larger Able 2029 cluster halo. At large radii, the cluster potential dominates, so a halo boundary can describe the cluster more than the galaxy. A lensing map would show mass contours that barely notice where the galaxy's light profile changes. So, largest by virial radius risks crowning the environment, not the central galaxy. That is not a mistake. It is a reminder that galaxies are nested inside larger bound structures. A fifth metric is influence rather than binding. Jets can define a galaxy's reach across intergalactic space. In radio maps, lobes can span megaparsecs, even when the host galaxy looks ordinary in optical light. The visual contrast is striking, an unassuming elliptical at the center, and then two faint wings stretching across cosmic emptiness. Those lobes are inflated by relativistic plasma launched near a supermassive black hole. Jet physics adds its own vocabulary. Magnetic fields help collimate the flow, while shocks and turbulence accelerate electrons that radiate synchrotron emission. The radio brightness depends on both the particle energy distribution and the magnetic field strength. As electrons lose energy, the spectrum steepens and the emission shifts to lower frequencies. So what looks like a small radio galaxy at one frequency can become a giant at another. The energy losses have a clock-like quality. High-energy electrons radiate away their energy quickly, so bright high-frequency emission marks relatively fresh acceleration. Older plasma can persist for much longer, but it glows mainly at low frequencies. That is why modern low-frequency arrays can reveal ghostly extensions beyond the edges seen in older surveys. The lobes can look like smoke in a dark room, visible only under the right light. In the wrong band, the same structure can vanish. Yet radio size has its own uncertainties, and they mirror the optical problem in a new form. We measure projected length on the sky, and projection can hide a longer true extent. A jet pointed partly toward us can look shorter, even if it is physically enormous. We detect lobes only where electrons still radiate at the observing frequency. Aging steepens the spectrum, so high-frequency surveys can miss the oldest, widest plasma. Environmental density also controls visibility, because confinement brightens lobes while emptiness spreads them thin. In a denser medium, lobes can be compressed, raising surface brightness and making edges easier to trace. In a tenuous medium, the same energy can fill a larger volume, lowering brightness below detection. So even the giants of radio can be undermeasured, mismeasured, or missed entirely. The map is not the object. The map is the object filtered through frequency, sensitivity, and instrument response. These forks in definition can reshuffle the largest list in opposite directions. By bright starlight, a concentrated elliptical with a sharp profile can win. By effective radius, a diffuse CD envelope can win even with similar stellar mass. By halo or virial radius, the winner may be a system whose dark matter dominates at huge scales. By jet influence, a black hole in a quiet environment can outstretch any stellar body. The universe offers multiple scoreboards, and each scoreboard measures a different physical story. Now confront IC 1101 directly. Its quoted size depends on which edge we mean. At conservative surface brightness limits, the visible body is already enormous by galaxy standards. In a typical visualization, The inner galaxy is a bright core, and then the light falls away into a broad, pale skirt. At more aggressive limits, the envelope can be traced farther, but systematics rise faster than signal. At the deepest claims, the light may include a large intracluster component that is not bound to the galaxy. So the honest statement is not one number. It is a range tied to definitions and data choices. Surface brightness thresholds are not arbitrary, but they are not universal either. Different surveys have different depths, different filters, and different control of scattered light. A redder filter can suppress some sky components, yet it can also change the contrast of old stellar populations. A threshold that is safe in one dataset can be misleading in another. Even the sky itself is structured, with gradients, airglow, and zodiacal light that must be modelled. In the outskirts of a seedy galaxy, a tiny sky error can create a huge false halo, so the largest galaxies live where measurement becomes an exercise in humility. Sky subtraction is the quiet villain in this story. To measure faint outskirts, we must estimate the background across a field that contains other faint structures. Those structures include faint galaxies, diffuse galactic cirrus, and the extended wings of bright stars. If the background model is too stiff, it subtracts real halo light and shrinks the galaxy. If it is too flexible, it preserves gradients that inflate the halo and enlarge the galaxy. The same raw image can therefore yield different largest conclusions, depending on reduction philosophy. This is why record claims are fragile. They are sensitive to the invisible steps between photons and catalogues. Selection effects then amplify the fragility. We preferentially discover compact bright objects because they stand out against noise and background. We miss diffuse halos because their surface brightness falls below survey limits, even if their total light is large. This bias has a simple visual analogy. A candle is easier to spot than a faint fog bank, even if the fog contains more light overall. We can also misclassify intracluster light as galaxy light, because both are smooth and extended. There is a second, subtler bias. Catalogue pipelines are designed to segment objects, and segmentation fails when the object has no crisp boundary. Deblending algorithms can carve a diffuse envelope into pieces, assigning parts to neighbours or to the sky. Conversely, a bright central galaxy can steal flux from nearby faint galaxies, inflating its measured outskirts. So the act of cataloguing can change the story. The largest systems are often the hardest to define in a database, so the census of the largest is biased toward what is easiest to detect, not what is most extreme. Deeper imaging can revise sizes upward, but it can also revise them downward by correcting systematics. That reversal is important, because it shows how errors can go in both directions. Either way, the record is provisional, and IC 1101's crown is not guaranteed. A future dataset might reveal a larger envelope elsewhere, or it might redraw IC 1101's boundary inward. The radio census has parallel biases. Interferometers can filter out large smooth emission, making giant lobes appear smaller than they are. That happens because an array samples certain spatial scales, and it can miss the most extended structures. Single-dish observations recover smooth emission, yet they have lower resolution and more confusion. Low-frequency surveys reveal older plasma, so the same object can grow in size when observed differently. Confusion from unrelated background sources can contaminate lobe edges and distort measured extent, so the biggest radio structures are also partly defined by instrument response and analysis choices. Largest known can mean largest detectable with current methods, and that is a moving boundary. If definitions are slippery, we still want limits. Physics should impose constraints on growth. For stellar bodies, growth is dominated by mergers, stripping, and accretion of satellites over time. The dominant channel for the most massive ellipticals is often dry merging, collisions with little cold gas and little new star formation. Dry mergers add stars without igniting bright blue disks, leaving behind smooth red remnants. But merger rates decline as the universe expands, because structures separate and infall slows. Dry merging also changes structure in a characteristic way. It tends to puff up galaxies, because stars are deposited at larger radii during violent relaxation. That is one reason effective radii can grow faster than stellar mass. A galaxy can double its size without doubling its light, simply by rearranging where the stars live. In the most massive systems, that rearrangement is part of the definition of largest. It is growth by redistribution as much as growth by addition. Dark energy accelerates expansion at late times, making new material harder to deliver to cluster cores. In the early universe, matter was denser, and gravitational collapse could pull material together more efficiently. As time passes, the cosmic web stretches, and the supply lines thin. So the supply chain that built giants becomes less efficient with cosmic time. The largest envelopes we see today are in part monuments to earlier epochs of assembly. Dynamical time sets another limit. To add stars at large radii, satellites must sync, disrupt, and phase mix, and those processes take billions of years. Dynamical friction is stronger for massive satellites because they stir a larger gravitational wake. Smaller satellites can orbit for a long time, shedding stars gradually into streams. The outermost additions are also the slowest to settle, because orbital periods grow with radius. So the biggest envelopes are time-limited, not only fuel-limited. There has been only finite time since the Big Bang to build and smooth such extreme outskirts. Cluster velocity dispersion adds a specific constraint. In rich clusters, galaxies move fast, so random encounters tend to be flybys rather than captures. A high relative speed makes it difficult for two galaxies to lose enough energy to merge. Mergers are suppressed for typical members, even though close passes are common. Those passes can still strip stars, heating and puffing up halos without creating a single remnant. The center is the exception, because dynamical friction can break massive satellites and deliver them inward. So the BCG can keep growing while the rest of the cluster is merger poor. This is why the largest stellar envelopes tend to sit at cluster centers, not in the outskirts. Even at the center, growth is not unlimited. As the cluster is processed, the pool of massive satellites shrinks, leaving smaller and less effective contributors. The remaining infill may be dominated by lower mass systems that add little to the bound core. Stripping can add intracluster light without clearly adding bound galaxy mass. At some point, additional stars are more likely to join the cluster's shared component than the galaxy's bound halo. So the galaxy can keep getting larger in light, while becoming less distinct as an object. The limit is not a hard stop. It is a gradual loss of separability. Jet growth has its own constraints, and they are different in kind. A jet's maximum extent depends on power, collimation, and how long the engine stays on. The engine is ultimately an accretion system, converting gravitational energy into outflow. It depends on duty cycle, because repeated episodes can extend or refresh lobes. A lobe can be a palimpsest, written over by multiple outbursts across tens of millions of years. It depends on ambient density, because dense gas slows expansion and increases radiative losses. It also depends on electron aging, because a lobe can exist physically while fading below detection. So a jet can be vast yet invisible, and invisibility can masquerade as absence. Void-like environments can enable extremes. Low density reduces entrainment and drag, letting jets remain coherent and lobes expand farther. In visuals, the lobes look like faint smoke plumes, widening as they push into a thin medium. Lower pressure spreads emission thin, which makes detection harder even as true size increases. So the same conditions that allow the largest radio extents also hide them from shallow surveys. This creates a selection trap. The most extreme objects are the easiest to miss. Now address cosmic expansion, because it is often misunderstood. Galaxies and clusters are gravitationally bound, so they do not expand internally with the Hubble flow. The space between bound members does not stretch in the same way as intercluster distances. Within a bound system, gravity and orbital motion dominate, keeping separations roughly stable over time. Expansion dominates on larger scales where gravity cannot bind structures against the cosmic stretching. So the universe's expansion does not tear IC 1101 apart, and it does not inflate its halo by itself. Expansion instead shapes the long-term supply of new material, reducing late-time growth opportunities. A useful way to picture it is to imagine two regimes on the same map. Inside the cluster, galaxies orbit like bees in a hive, and the hive does not expand with the meadow. Outside, the large-scale pattern of galaxies recedes, and the distances between clusters grow. The boundary between these regimes is not a fence. It is set by whether gravity can overcome the expansion on a given scale. That is why the language of bound is central to the story of size. This is where the title's provocation must be confronted calmly. IC 1101 could swallow the local group in a halo sense, depending on how halo is defined. It could overlap the region containing the Milky Way and Andromeda if we count diffuse outer components. That mental picture is useful because it forces us to compare scales we normally keep separate. But it cannot swallow the universe, because the universe is not an object inside another object. The universe is the total space-time and contents, and it has no outside volume to be contained. The phrase is poetic scale, not cosmological reality, and the difference is the lesson. We use that lesson to separate three ideas that sound similar. Size in starlight is where long-lived stars are detectable above background. Size in binding is where matter remains gravitationally attached to a specific potential. Size in influence is where energy and momentum from a nucleus can still alter the surrounding medium. A single system can be small by one metric and enormous by another. So largest galaxy is not one claim. It is a bundle of claims, each tied to a physical question. The climax is not a number. It is the realization that our categories are the fragile part. IC 1101 does not break physics. It breaks the assumption that objects have clean edges. Giant radio galaxies do not break physics. They break the assumption that a galaxy's reach equals its starlight. The universe does not just contain big things, it contains multiple ways for bigness to exist. Now the speculative frontier, because the record is not closed. There could be CD galaxies with even larger diffuse envelopes, hidden below current surface brightness limits. Future surveys with better sky control could reveal halos extending farther than we currently trust. Those advances may come from improved baffling, better calibration strategies, and careful modelling of scattered light. Improved kinematics could separate bound halo stars from intra-cluster stars, changing what we count as the galaxy. A velocity distribution can reveal whether stars move with the galaxy's potential or with the cluster's deeper field. So IC 1101 may be the largest known today, but not the largest that exists. There could also be radio structures larger than current champions. A long-lived engine in an exceptionally thin environment could inflate lobes across even larger fractions of a void. Low-frequency mapping could reveal ancient plasma that current catalogues miss. Projection could hide true lengths, so some giants may already be larger than we think. In that case, the largest object might be waiting in the data, mismeasured by geometry, so the record could be broken by better sensitivity, better frequency coverage, or better geometry. Yet even speculation must respect limits. The universe has finite time since the Big Bang, so growth must fit within cosmic history. Fuel is finite because accretion and mergers depend on available matter and on delivery pathways. Feedback is self-limiting because powerful outflows can reduce future accretion onto the central engine. Expansion reduces new infall at late times, and that throttles both galaxy assembly and long-term feeding. So the largest structures are not arbitrary. They are what gravity and time can assemble under real constraints. This brings the narrative home to human intuition. We want a single edge because edges make objects feel graspable. The cosmos offers gradients instead, and it forces us to think in distributions and probabilities. Following IC 1101 to its faint outskirts teaches us how measurement and definition shape reality. Following giant radio galaxies to their lobes teaches us how influence can outscale mass. In both cases, the largest things do not end the story. They expose the rules that build everything else. Transition to the final chapter. We have chased the biggest galaxies and the farthest jets, and the prize is clarity. The resolution is not a new record, but a better map of what largest can honestly mean. We come back to IC 1101, not as a headline, but as a mechanism made visible. It sits at the centre of Able 2029, where gravity keeps delivering material inward along cosmic structure. In that deep potential, time does not just pass, it accumulates, and the centre keeps score in starlight. The numbers still matter, because they anchor the intuition we are trying to repair with careful scale. By conservative starlight, IC 1101 reaches roughly 550,000 light-years across in visible extent. That figure already assumes deep imaging, because the outer light is thousands of times dimmer than the sky. By the faintest claimed envelope and shared glow, its halo can stretch toward 4 million light-years. That outer reach is not a crisp border, and it is not guaranteed to be bound as one coherent system. It is a gradient where galaxy light, intra-cluster light, and measurement thresholds overlap in slow transition. If you could see it with your eyes, the center would look ordinary. Then the edges would refuse to end. The brightest core would fade into a soft pearly haze that keeps extending, almost imperceptibly, into the cluster. This is the first resolution of the central question, and it is quieter than the title suggests. IC 1101 is not an exception that breaks the universe. It is a product of its address and history. Cluster centers are where orbits decay, satellites disrupt, and mergers become a long-term bias. Dynamical friction drags the most massive companions inward, even in a fast cluster core. In plain terms, heavy galaxies plow through a sea of dark matter and stars, and they lose orbital energy. That energy is not destroyed. It is transferred into the surrounding background, heating and stirring the cluster's core. Over time, the bigger satellites spiral inward, and the central galaxy becomes the place where mass tends to settle. Dry mergers add stars without rebuilding disks, and they deposit much of that mass at large radii. Because the incoming galaxies are gas-poor, they do not trigger bright new starbursts that would redraw the structure. Instead, their old stars are redistributed, puffing up the outskirts and thickening the envelope like layered fog. Tidal stripping adds another component, peeling stars into streams that later smear into a smooth envelope. At first, those streams are sharp, thin arcs and shells that wrap around the galaxy like ripples on dark water. Then the cluster's tidal field stretches them, and orbital precession mixes them until the pattern dissolves. Over billions of years, countless small disruptions build a diffuse halo that looks serene. The serenity is the evidence, because only time can erase the sharpness of debris and make it look inevitable. In deep images, that calm light is the fossil record of violence, written in gradients instead of scars. Abell 2029 supplies the environment that makes this possible, and it also hides the boundary. The cluster is filled with hot plasma at tens of millions of degrees, glowing in X-rays like a submerged ember. Hot X-ray gas strips cold fuel, so growth shifts from new stars to rearranged old ones. Ram pressure and tidal heating suppress fresh disks, which is why central galaxies become smooth ellipticals and CD giants. The cluster's shared light becomes a reservoir, and the central galaxy becomes its brightest knot. Intracluster light is not just extra glow, it is made of real stars on wide orbits through the cluster potential. Those stars can come from shredded dwarfs, from the outskirts of spirals, and from merger debris flung outward. At some radius, the same photons can be read as galaxy outskirts, or as cluster background. That ambiguity is not a failure of language, it is a physical coupling of systems. The central galaxy and the cluster are nested structures, and their outskirts are literally interwoven. IC 1101 grows because the cluster grows, and the cluster glow grows because galaxies are ground down. If you pan across the core, the light would look like a tide line, subtle bands where definitions stop working. The second resolution is harder, because it asks what kind of largest we mean. Astronomy has always wrestled with this, because what we can measure depends on wavelength, depth, and definition. Early catalogues ranked galaxies by apparent size on photographic plates, where faint halos vanished into emulsion limits. Modern surveys push deeper, but they introduce new problems of scattered light, flat fielding, and sky subtraction. So, largest is never just a fact, it is a fact filtered through an instrument and a method. If we rank by starlight assembled into a single dominant stellar system, IC 1101 remains a contender. Its size is built from hierarchical merging in a deep potential, not from a single dramatic event. Hierarchical growth is the quiet rule of the cosmos. Small things combine, and the biggest places collect the leftovers. If we rank by gravitational domain, the story shifts toward the cluster halo itself. Dark matter sets the main potential, and the galaxy is nested inside a larger bound structure. The virialized region of Abell 2029 is vastly larger than any galaxy's starlight, and it holds the real mass budget. If we rank by influence rather than binding, the scoreboard changes again. Influence can mean heating gas, shaping magnetic fields, or altering where future stars can form. That kind of reach is not drawn in optical light, and it does not respect the edges of stellar halos. This is where giant radio galaxies enter as a different kind of largest. Their hosts can be ordinary ellipticals, yet their jets draw structures across intergalactic space. The central engine is a supermassive black hole, fed by accretion that converts gravity into directed power. Magnetic fields anchored in the rotating disk collimate plasma into twin beams, narrow at first, then widening with distance. Porphyrion-like systems show lobes spanning tens of millions of light-years in radio emission. In radio maps, those lobes look like ghostly wings, brightened at the edges, dim in the middle and fading into noise. That scale is not a stellar halo, and it is not a virial radius, and it is not a cluster core. It is a footprint of energy, momentum, and magnetized plasma delivered far beyond the galaxy's light. The lobes inflate like bubbles, pushing against the surrounding medium until pressure balance slows their growth. Shocks and turbulence can re-accelerate particles, while older electrons cool and dim through synchrotron losses. So the film's two largest narratives do not cancel each other. They occupy different rulers. IC Elena 1 is among the largest stellar assemblies we can plausibly define. Giant radio galaxies are among the largest outflows a single nucleus can sustain. One is a monument built from stars, the other is a reach measured in fields, particles, and time. The central question asked how anything grows so large, and what largest even means. The answer is not one number, it is a synthesis of three processes that cooperate across cosmic time. First, hierarchical merging in deep potentials builds the biggest stellar bodies at cluster centers. Gravity funnels mass along filaments, and the center becomes a long-lived accumulation point. Those filaments are not visible ropes, but statistical highways where dark matter and gas fall inward more often. In simulations, the densest nodes keep gaining mass, because they sit where multiple streams intersect. Second, diffuse halos are built from countless disruptions, where stripped stars become a shared component. The halo grows by addition and by redistribution, and the edge becomes a probability. A star near the outskirts may belong to the galaxy by brightness profile, yet belong to the cluster by orbit. Third, rare black hole episodes export energy outward, painting intergalactic space with radio light. Those episodes can be persistent rather than explosive, and persistence is what makes giants. A jet that stays on for tens of millions of years can outrun the fading of its own particles. A jet that flickers too quickly leaves fragments, relic lobes that drift, cool, and become hard to detect. The black hole piece matters because it solves a different scaling problem. A compact engine can control a structure millions of light years long without violating physics. The jets are launched outside the event horizon, then guided by magnetic fields and pressure balance. Close to the black hole, the flow is relativistic, and its apparent brightness can depend on viewing angle. Farther out, the jet entrains ambient material, slows down, and dumps energy into lobes and hotspots. Their maximum reach depends on power, duty cycle, and the density of the surrounding medium. Thin environments allow expansion and coherence, even while they lower surface brightness and hide edges. So the largest radio structures are partly an environmental achievement, not only an internal one. They also remind us that visibility is not the same as existence, because old plasma fades. Low frequency survives longer in the spectrum. Even then, the boundary is statistical, where signal falls below noise, not where physics abruptly stops. This is the reconciliation that earlier chapters promised, and it is also a warning. Our categories are not wrong, but they are incomplete when we treat them as a single contest. Starlight traces where baryons settled into long-lived orbits after mergers and relaxation. Relaxation is a technical word for mixing, but the plain meaning is simple. Chaos eventually looks smooth. Dark matter traces the binding scaffold that makes clusters and halos stable over cosmic time. We infer it through galaxy motions, hot gas profiles, and gravitational lensing that warps background light. Jets trace where a black hole can deliver feedback, changing conditions far beyond the stellar body. That feedback can prevent gas from cooling, regulate future accretion, and keep cluster cores from collapsing into starbursts. Each is a real structure, and each has an edge that is defined by different physics. When those edges disagree, the universe is not confused. Our language is. The disagreement is not a flaw. It is a clue that nature builds with overlapping components, not tidy layers. We can now answer the hook without deflating it. The Milky Way is not small, it is simply local to a scale we evolved to trust. Our galaxy is about 100,000 light-years across in starlight, and that is already immense. It contains hundreds of billions of stars, and it sits inside a halo that extends far beyond the disk. That halo includes dark matter, sparse stars, and globular clusters on wide orbits that take billions of years to complete. What fails is not the Milky Way's grandeur, It is our intuition about what counts as a boundary. We tend to treat the bright disk as the whole object, because brightness is what our eyes and culture prioritize. When we compare it to IC 1101's visible extent, the Milky Way feels like an inset. When we compare it to a 4 million light-year envelope claim, it feels like a rounding error. When we compare it to Porphyrion-like lobes, it feels like a point inside a line. The lesson is not humiliation, it is calibration. Calibration means accepting that the universe's typical units are not human units, even when the images look familiar. Calibration leads to the final reframing of scale. The universe has more room than our metaphors assume, and more time than our instincts allow. Gravity does not aim for moderation. It amplifies small differences into large outcomes. A slightly denser region attracts more matter, then becomes denser still, an iterative process that rewards early advantage. Time does not merely age systems, it integrates countless events into smooth-looking extremes. Environment does not decorate the story, it sets the boundary conditions that decide what can grow. IC 1101 is what happens when a cluster center keeps receiving mergers and stripped starlight. A giant radio galaxy is what happens when a black hole keeps its aim and keeps being fed. Neither is a miracle, and neither is a violation, and both are natural endpoints. The extremes feel shocking only because our sample is small, and our thresholds are high, yet the record book remains unstable, and that instability is part of the meaning. The faintest outskirts of CD envelopes live where sky subtraction and scattered light can mislead. A tiny error in background estimation can create or erase a halo that spans hundreds of thousands of light years. Starlight from bright foreground stars can scatter inside optics, producing artificial glows that mimic real structure. The widest radio lobes live where interferometers can filter out smooth emission and miss the true scale. Radio arrays are exquisitely sensitive to certain angular scales, yet blind to others, depending on baseline coverage. Low-frequency surveys can reveal older plasma, and deeper optical imaging can reveal dimmer halos. So today's largest known is partly a statement about our thresholds, not nature's ceilings. As instruments deepen and surveys widen, the champions can change without the physics changing. Tomorrow's second place may already exist, just below the surface brightness we can trust. And when it emerges, it will not rewrite the rules. It will simply show how far the rules can run. That leaves a lingering mystery that does not need a dramatic twist. If boundaries are gradients, then largest is always conditional on how we draw the line. We can improve definitions with kinematics, lensing, and multi-wavelength maps, yet edges will still blur. Kinematics can reveal whether outer stars share a common rotation or dispersion pattern, or whether they move with the cluster. Lensing can map the mass distribution without caring about light, but it still returns a smooth field, not a sharp wall. Some stars at the outskirts of IC 1101 may orbit the cluster more than the galaxy. Some radioplasma may persist long after it fades, still magnetizing space we no longer see. Even when the electrons cool, the magnetic structure can remain, a faint memory imprinted on the intergalactic medium. The cosmos refuses to be neatly bounded, because its structures are processes, not objects. A galaxy is not a statue. It is a flow of matter through time, briefly coherent, then slowly redistributed. Transition, so the final chapter does not end with a winner, but with a method. We stop chasing a single crown, and we watch how gravity, time, and environment build extremes. IC 1101 becomes a case study in assembly, where the boundary between galaxy and cluster dissolves. Porphyrion-like giants become a case study in influence, where a nucleus extends reach beyond starlight. Together they answer the central question by splitting largest into honest, physical meanings. Largest in stars is not the same as largest in binding, and neither is largest in feedback. The universe does not just contain big things, it contains multiple ways for bigness to exist. And once you see that, the argument about records becomes less important than the architecture behind them. In the end, the quiet conclusion is also the biggest one. IC 1101 does not swallow the universe, but it shows how our words can overreach. Giant radio galaxies do not redefine galaxies as single objects, but they redefine what a galaxy can do. Records will fall because our maps will improve, and the faintest structures will keep emerging. The true lesson is not the record. It is the process that keeps producing new extremes. A cluster core will keep collecting, a halo will keep diffusing, and a black hole will sometimes keep firing. Those are simple rules, and they are sufficient to build shapes that feel impossible from the inside. End beat. Hold on the faint glow of a cluster core, then on a radio lobe fading outward. Let the optical image linger until the eye adjusts, and the dim envelope becomes a presence rather than an absence. Then shift to radio color, where the lobe is bright at first, and then thins into a whisper of structure. Edges dissolve into background, definitions soften, and the cosmos remains larger than our categories. We leave with the sense that the universe is not trying to impress us. It is simply following its rules, and the rules are enough to build the unimaginable. We began with a simple zoom out from Earth's thin air to the Milky Way's halo, and watched distance turn into physics. By the time IC 1101 filled the frame, scale stopped being a number and became a negotiation between light, gravity, and time. IC 1101 is immense in starlight, but it is even more revealing as a process, a central dominant galaxy assembled inside Able 2029's deep potential well. Dynamical friction drags heavy neighbours inward, dry mergers stack old stars onto the outskirts, and tidal stripping smears once distinct galaxies into a shared, ghostly intracluster glow. That glow is where the story gets slippery, because galaxies do not end like islands, they fade like weather. At the surface brightness limits where sky subtraction, scattered light, and telescope optics start to matter, the edge can shift by hundreds of thousands of light years, so we learn to carry three rulers at once, each tied to different physics and different evidence. There is the luminous extent drawn by isophotes and limited by photons. There is the diffuse stellar halo and intracluster light, written by tides and mixing, and there is the dark matter domain, inferred through velocities, lensing, and hot X-ray gas. In that framework, IC 1101's conservative visible span, roughly 500,000 light-years, is only one honest answer. The debated multi-million light-year envelope is another answer, and it forces the harder question of whether those outer stars are bound to the galaxy, or already citizens of the cluster. Able 2029 itself became part of the definition, a cosmic city whose mass is mostly dark matter and whose streets are filaments feeding the node. Its intracluster medium, tens of millions of degrees hot and bright in X-rays, strips galaxies of cold gas, suppresses new star formation, and leaves growth to rearrangement rather than creation. And then the meaning of size broke open again, when we followed black holes instead of stars. Giant radio galaxies showed that a fairly ordinary-looking elliptical can project jets and lobes across intergalactic space, building structures millions, even tens of millions, of light-years long. Those radio giants are not bound the way a stellar halo is bound, but they are real architecture, shaped by magnetic fields, shocks, and long duty cycles. They also reminded us that the record book depends on our instruments, because faint optical halos can be erased by imperfect background models, and diffuse radio lobes can be filtered out by the very arrays designed to detect them. So the biggest revelation was not a single champion, but a better map of what largest can honestly mean. In the universe, bigness is plural, measured in starlight, in binding mass, and in influence, and each measure tells a different story about how structure grows. Along the way, we kept returning to a boundary that refuses to hold still. The outer light of IC 1101 and the intracluster light of Able 2029 blend continuously, and the cleanest divider may not be visual at all but kinematic, whether those stars orbit the galaxy's center or the cluster's broader potential. Even the most dramatic radio lobes raised a parallel puzzle about edges and persistence. The visible synchrotron glow fades as electrons age, yet the underlying plasma and magnetic scaffolding may linger, meaning the true structure can outlive the light we use to find it. Taken together, the chapters point to a quiet conclusion, one that feels less like a trophy ceremony and more like a lesson in cosmic bookkeeping. The universe does not break physics to build giants. It uses gravity, environment, and time, then dares us to define what we are seeing. And that is why IC 1101 matters, even if its crown changes. It sits at the intersection of our three rulers, where galaxy becomes cluster, where measurement becomes interpretation, and where scale becomes a question rather than an answer. So what does largest galaxy even mean? And did IC 1101 really threaten to swallow everything we call home? The answer is that it never swallows the universe. It swallows our intuition. because largest depends on whether we mean starlight, bound mass, or far-reaching influence. IC 1101 is colossal by any everyday standard, but its greatest size is conceptual because it exposes the blurred border between a galaxy's halo and a cluster's shared light. And when we compare it to giant radio galaxies, we see that a galaxy can be small in stars, yet enormous in the space its black hole can touch. In the end, the universe doesn't just contain big things, it contains multiple ways for bigness to exist, and each way rewrites the edges we thought were solid. IC 1101 and the radio giants don't break the rules, they break the words, and in that crack our sense of scale finally has room to grow. Maybe the most honest largest is not a number at all, but a question we can keep asking with better light, better maps, and more patient definitions. Because out there, the boundary between what is seen and what is real is not a line, it is a frontier. If you want to follow that frontier, watch what the next deep optical images, kinematic surveys, and low-frequency radio maps reveal, and be ready to let the record change.